Alrighty, y'all. Welcome to the stream. This is, well, I am Andrew Smith, Twitch name Linguifex, and today we are going to be talking primarily about recursion. I noticed that we've already got a few of you in the chat, so I'd like to take some time to welcome you to the stream. If you are more experienced at this whole streaming thing than me, then please let me know if I'm doing anything wrong, or if you can't hear or see anything. This is my first time doing this, so hopefully everything will run completely according to plan. But yeah, so some of you have already noticed, if you were in the chat and reading everything, that our music for today is a selection of Bach. And this is kind of, there are several layers of meaning to this. The biggest one is mainly just that I am an organist and really like Bach. As you can see behind me, I've got an organ. And actually up on the music stand is a Bach Prelude and Fugue BWV 535, the one that you heard right when you joined the stream. However, the second kind of part of this is that Fugue is, in my opinion, the most recursive form of music there is. You have essentially a theme that is repeated in all sorts of various ways with slight variations, some over each other, some nested, and so it really is kind of almost recursive music. In that way. And so yeah, so we've got some Bach Fugue broken up slightly by some preludes and fantasias and a few other things just to make things sound nicer, and all of the music is public domain so that I don't get DMCA'd. Rest in peace to YouTube DL. Anyway, so yeah, so the meat of today is going to be going through some practice problems, kind of like ones that you may have seen before, and ones that you may see in an exam if you're in an intro data structures course. And then we're going to take it a step further just to make things a little bit more interesting and add some depth to the work that we're going to be doing today. So yeah, so why don't we go ahead and get right into this by looking at our first problem. And shout out to NooshBH in the chat who said stream quality is great. Thank you, thank you. I'm glad that everything is working thus far. So yeah, let's go ahead and switch to the desktop view and get started. Alrighty, so the first problem that we are going to be looking at today is a problem that I call compressed Morse code. Now, the compressed Morse code problem is really a fairly interesting problem. It deals with some archaic technology, which I'm always a huge fan of, that we've now adapted to a computer format, in addition to having a really cool kind of implementation that we're going to go through. Question in the chat, will this be recorded? Yes, this is actually being recorded right now. The VOD will be available very shortly thereafter, and I'm also simulcasting, so this will be available on YouTube in just a little bit. But yeah, so this problem deals with Morse code. Now, Morse code, just for a little bit of background, is a form of communication that was initially devised in order to be used with a telegraph. So a telegraph is this kind of ancient telecommunication device, well, not ancient, but, you know, from the last century, telecommunication device that was used before we really had high quality enough transmission to transmit things like a human voice, as you would with a telephone. And so a telegraph is a device with one button. It has essentially two possible sound outputs, on and off. And the way that people communicated with this telegram, this kind of binary format, was to send different lengths of pulses back and forth. And so essentially you would have two kind of different, not tones, but two different lengths of tone. So one would be very short, called a dit, and one would be a little bit longer, called a da. If you've ever seen a movie, I'm sure you've seen a movie where someone was using a telegram, maybe sending an SOS, which sounds something like dee-dee-deep, which is 3 dits, followed by 3 DAWs, followed by 3 dits, where 3 dits is the letter S, 3 DAWs is the letter O, and then 3 dits for the letter S again. And so that's just a little overview of how Morse code works. And in this problem, we're going to be translating some Morse code into English. And now, the code to actually translate Morse code isn't incredibly interesting, so to kind of simplify the process, I've written this class called MorseMap. And what MorseMap is it's basically just, well, it's what it sounds like. It's a map from Morse code strings onto Latin alphabet characters. And now it's a little bit more interesting than just a map, actually, in that the way that it's implemented is as an array-based binary tree, or which some people would call a binary heap, where essentially on each dit we navigate to the left of the root, on each dot we navigate to the right of the root. It's kind of an interesting way to implement this in a really compact amount of space. And so this is the class that we're going to be using to do the actual Morse code translation. You can see it provides all of our very standard map interface methods, so we should be able to interact with this just like we would a normal map. And now this problem tells us that we are going to be given a string of Morse code, and so it's just going to be literally a string containing exclusively dits and DAWs. Those strings are going to look something like this. So this is a test file that I generated. These are essentially the test cases for this method that we're going to be writing. Dits are represented by periods, DAWs by hyphens. So we're going to get one of these strings, guaranteed that it contains a permutation of the Latin alphabet as used for English. And so it's going to contain 26 Latin alphabet letters, A through Z, in some randomized order. And our goal is to take in this Morse code string, convert it into the permutation of the alphabet, and then return that permutation of the alphabet that we have. And so yeah, so that's really what we're going to be doing here today. We're going to use the Morse map in order to actually perform the translation. And a kind of interesting aspect about this problem is that there can actually be multiple solutions for a given input. And so each one of these inputs here doesn't actually just convert to a single alphabet. It may convert to a bunch of different alphabet permutations based on how we segment letters. But our goal here is just that we want to return one of them. And now before we start actually getting into writing the code for this, which we definitely want to do in just a second, I would just like to invite everyone that, of course, at any point while we're going through all of these things, if you have any questions, totally feel free to post them in the chat. I will be monitoring the chat, so you should be able to see everything that's going on there and kind of keep up with what we're talking about. And I'll make sure to kind of read out chat messages as well, just so that people who aren't viewing this on Twitch will get the benefit of those questions. So yeah, let's go ahead and start. So I know that I'm going to be getting this Morse code string. Oh, great question. So Prince Logic asks, wait, so is that random Morse code or does it actually translate to words? Yeah, so each one of these translates to a permutation of the Latin alphabet. And so each one of these translates to a string containing all the letters A through Z in some order. It could be directly in order, it could be in some jumbled order, but it's going to convert to a valid string containing 26 Latin alphabet characters. So yeah, so it's not completely random, but it doesn't necessarily translate to words. That is another interesting problem that we could do, but it's much more complicated, and way more complicated than anything that anyone who's in this kind of review is probably going to see. And we've got another question. NewsBH, what theme for IntelliJ are you using? Yeah, so this is the Carbon theme for IntelliJ. If you go on the IntelliJ theme gallery, it's actually pretty far down. But yeah, I also think that it's pretty nice. It's very easy on the eyes, works in daytime and nighttime. I'm kind of a red and purple and pink aesthetic type of person, as you can see by the background of the stream today and just kind of everything else. In addition to the fact that I'm actually partially colorblind, and so I actually cannot see, I cannot distinguish between different shades of blue and green quite as easily, and so having these colors is actually partially an accessibility measure as well. And so yeah, if you wanna use that theme, go ahead and check it out. It's called Carbon on the IntelliJ Marketplace. Super cool. Oh yeah, and Shuttlemax, how are spaces between words shown in Morse code? And that's a really great question. They kind of aren't. There's no Morse code character that converts to a space. Usually what will happen is, so single letters in a word may be separated by a brief pause, and words will be separated by a slightly longer pause. And so yeah, Morse code cannot directly actually encode messages like we would, talk about, if we're speaking or writing them down. We have no way to encode a space. Punctuation is encodable, but wasn't used quite as frequently as we might like. And so, spaces are not really something we're going to be worrying about here, and there wasn't a good way to indicate them in Morse code other than having a slightly longer pause. And, that seems really weird to us as English speakers, but historically it's not actually that strange. I mean, if you ever look at a Roman inscription, then you'll notice that when they were writing, their words just kind of went together like this. So this is just the beginning of the Aeneid, arma virumque cano Troiae qui primus ab oris. And you'll see there are no actual spaces here. And you're like, well, that's super hard to read. But if you know the language, and if you're used to reading like this, it's actually fairly easy to segment. A more modern example is Mandarin Chinese, or any language that's written using the Hanzi script. Doesn't have spaces either. So yeah, it's workable. Anyway, getting a little off track here, and yes, yeah, I do cite the subreddit we got this from, r/dailyprogrammer. It's a really cool subreddit if you want some interesting practice problems for programming. I encourage you to all check it out after the stream. So yeah, so let's get into this. And so, just kind of looking at this problem, I know that I'm going to need a few things. I know that I'm going to need, and let me put this back so that IntelliJ doesn't get mad at me. I know that I'm going to need the Morse code string we're decoding. I'm definitely going to need to hold on to that Morse map, because I need to have some way to actually translate these things. I'm probably going to need some way to store where in the Morse code string I currently am, so I don't restart decoding on every single recursive call. And so I'm just going to say probably a Morse code index pointing to some character in Morse. And that'll work in terms of if we're blindly decoding. So we're just trying to decode to some valid Latin alphabet string. And yeah, and that would work perfectly fine. But we do have this kind of odd constraint here that we know that this string has to be a permutation of the Latin alphabet. And so we cannot allow repeated characters in the string. Each character has to be unique. And so in that case, I'm going to need to have some way to keep track of the characters I've used so far. And so yeah, and so this is kind of the initial setup for our problem here. These are the things that we're going to need as we implement our recursion. And looking at what we've got here, I noticed that this method here, this recursive method, our public interface, only takes 2 parameters. And, you know, we could get around this. We honestly could. We could get around this by, you know, making sure that the strings are unique every time we return one and passing substrings of Morse at a time, and that would work. But quite honestly, it's a little bit clunky, and it's going to be really slow. So what I'm going to do is I'm going to come up here, and I'm going to just start off right off the bat by writing a helper method here. So I'm going to say private static string. We want to return the same thing that we're returning in our main method. And, you know, I'm just going to call this, find alphabet. Why not? And we know that we're going to need to take in the same parameters that are in decode alphabet. We know we're going to need those, so I'm just going to go ahead and plonk those up there. In addition to the fact that I need an index, so let's just call that something like Morse index. And now I'm going to need a way to track the characters I've used. And there are a lot of different ways to do this. We could use a set and check for membership, but that's, you know, that's not super great. I don't really like doing that. We're either going to have to compute hash codes or navigate a binary tree. That's suboptimal. But what I would like to do then is we know that since there are going to be, at max, 26 different characters in the string, I'm just going to pass a Boolean array of length 26. I'm going to call that chars used. Okay, great. And so here is our recursive method, and for now, I'm going to return null. Because now, before I forget, and this is something that I forget very frequently as I'm writing code, I'm going to actually call the recursive method. This is something that I have done many times. I've had coworkers and friends who've done many times that they spend all this time writing this recursive method, and they're like, it must always be failing, because I'm always returning null or returning 0 or returning some default value. And then after 30 minutes of debugging, you come back and you're like, oh wait, I am an absolute idiot. I forgot to actually call the recursive method I just wasted all that effort on. And so yeah, that's not something we want to do. So what I'm going to do is just start off by returning find alphabet, gonna pass in the Morse code string, gonna pass in the Morse map. We're of course gonna start at index 0, we have to, and then characters used is just gonna be a throwaway Boolean array of size 26, right? The number of characters that we have in the alphabet. And now I know that some of my students are watching this stream, and you're like, well, wait a second. Hey, that's a magic number. You would count points off for that. And, you know, you're right, I would. So let's fix it. So let's say private static int num letters is 26. There we go, great. And we'll just go ahead and head down into this method, substitute that out, and there we go. Now we're not going to lose any points on this. Oh, and of course we're going to declare it final. So private static final int. There we go. Alrighty, so now let's go ahead and do our recursion. So when we're doing recursion, as always, we want to think about a few things. What is our base case? More simply, what are our base cases? Sometimes we might have multiple. And below that, what's our success cases? What are our failure cases? So in essence, when do we know that the thing worked? And when do we know that the thing didn't work? And we likely have to try something else. And then the hardest one to think about is the recursive case. So this is essentially how we're going to take a further step in order to get ourselves closer to the base case. And now I'm going to start off by writing some base cases. So I know that in this problem, we know that everything worked when every character has been used, right? So every character in the string has been used, and we are at the end of the string. In other words, we used every single Morse code character that we could, and we have translated that into every Latin alphabet character. So I'm just going to say every Latin character has been used. And so we're going to start off by writing that case. And so what I'm going to say is, alrighty, so if we are at the end of the string, and so if Morse index is equal to Morse.length, then we know reach the end of the string, and now we need to evaluate if our choices have worked. And so now we have to do some introspection and figure out, you know, have we made some horrible choices in the past that we're going to need to rectify in the future, or are we happy with where we're at and are keen on staying at our current position? So the way we're going to do that is we'll start off by writing our success case. We're going to say, alrighty, and so I need to evaluate how many characters have been used. And so honestly, one way that I could do this is to write a for loop, right? I could just say, you know, int num used equals 0, and then loop through the Boolean, you know, for Boolean used and chars used. And, you know, if used, I could increment num used. But notice that we're going to be running this loop every single time in the base case. And moreover, quite honestly, every character being used seems like a pretty easy thing that we could actually track as we go, right? Because we're going to use a character, presumably, at some point, and so we could actually just track the number of characters we've used. And so what I'm going to do is get rid of this and add a parameter for the number of characters that we have used so far. I'm going to pass that in to our method, starting with a value of 0. And so now this code becomes super simple. All I've got to do is say, alrighty, so if the number of used characters is equal to 26, so is equal to num letters, then we know that we have a valid decoding. Decoding every character was used. And what I'm going to do is I know I'm going to have to return something here. And the way that I could do it is build a string up as we go through the method. And so I'd add a character, pass that in as another parameter that contains the translation. But, you know, that seems like we would honestly be generating a lot of strings that we don't necessarily need to, right? Every time something fails, we would have a bunch of strings that we made that we're just going to toss anyway. And so that seems inefficient to me. What I'm going to do instead is build the string as we go back up the call stack. And so what we're going to do is, as we return, each time we're going to return the string that was generated from everything at the current recursive level and below. And so that's how we're going to be building our strings as we go. And so what I'm going to do here is I'm going to say, well, because this position, Morse index equals Morse.length, does not correspond to a character, and let me make sure my keyboard layout is correct, we're going to return an empty string. Say, hey, we return something, gotta build a string, gotta build a string, but, you know, there's no character that corresponds to this position, so, you know what, just return nothing, and we'll deal with it later. Otherwise, if Morse index is equal to the length of the string, but we haven't used all the letters, then something went wrong. And we must fail. So we're going to say we have to fail. And the way that I'm going to fail is by returning null. Anytime we fail, we always want to return some value that could never actually be generated by the method that we're writing. And oftentimes, if we are returning a reference type like string or array list or hash map or something like that, null is going to be our best candidate. And yeah, welcome to the few more people who have joined in. Yeah, let's make sure that we don't dox anyone in the chat, please. Anyway, moving forward. So now, to me, it seems like we've got both our success and our failure case written. And so, to me, this seems like, all right, well, this must be our base case is done. And so now, the only thing we have left is the recursive case. And for this problem, that's going to be a little bit harder. So the thing that we want to think about, as always with recursion, is what is our overall goal, and what is a single step that we could potentially take to get closer to that goal. And so our overall goal in this method is to use every single character from the Morse code string to translate to a Latin alphabet character. And so every single character in this string is going to be a Latin alphabet character. That is our overall goal. And so the thing that we can do to take one step closer to that goal is to try and translate a few or even a single Morse code character to a Latin alphabet letter. And so what we'll do is we're going to go ahead and kick that off. And so what we're going to do is we're going to say, okay, so now what I want to do is I want to try every possible Morse code character from the current position in the string. And so I'm going to try and go through every single character that I can. And now, unfortunately, this is something that is kind of prerequisite knowledge that's required about Morse code. And that is that the letters in Morse code, and we'll call this max blips, can be at most 4 blips long. A blip being a dit or a daw, a long or a short. And so yeah, the Latin alphabet letters in Morse code are at most 4 characters long. And so we know that any combination of 1 to 4 blips from the Morse code string could potentially translate to a Latin alphabet letter. And so the way that we can do that is say, okay, so and I'm just going to run a for loop to run through all of these different lengths. Right, at our recursive step, we want to try every possible option we can, and in this case, that's going to be a number of blips from 1 to 4. It's going to say int Morse, let's call it Morse length, something like that. It's going to go from 1. And we want to run that up to and including the maximum number of blips that we have. And each time, of course, we're going to increment the length. Okay, great. And so now what we want to do is we want to actually translate the character with that length into a Latin alphabet letter. So the first thing I'm going to do is I'm just going to grab the letter from the Morse code string, and I'm just going to use that using string.substring. And so it's going to be morse.substring. And we're going to start at the current index and run this up until the end. And now, the thing to note about the string.substring method is that the beginning of the range is inclusive and the end of the range is exclusive. So it's a lot like a for loop when we write it with less than, that the last number that we pass, the limit, isn't actually going to be included. And so if we want a single character from the string, then we would say that we want to run that up to, but not including, index morse index plus 1. And we can generalize this by saying that we want to add morse len to get the Morse letter of that length into a substring. So the next thing we've got to do is we actually need to translate the Morse letter into a Latin alphabet letter, right? Because so now that we've got the Morse code string, we've got to actually convert that into something that we can read and use. And so what I'm going to do is grab this from translator. So I'm going to say, okay, great. So this is going to be translator.get. Remember that Morse map is just a map from string to character. That's all it is, with some pre-filled values. And so the key we're going to pass in is just the Morse code letter. And that's it. And so that's how we can do our translation using this map. And that's, you know, the cool thing about having a dedicated class for this is that now you don't have to sit and watch me fiddle with Morse code translation for 5 hours, because that is probably what would happen if we didn't do this. Okay, and so now we do run into the kind of odd situation that there are actually some combination of dits and daws in certain orders that might not translate to an actual letter. And so what I need to do is I need to actually make sure that what I got out is a valid letter. And so the way I'm going to do that is I'm going to say, okay, so if... Oh, didn't mean to comment that, sorry. If Latin letter is not equal to null, then I want to do some stuff with it. And you'll note here that my use of the character type here for this letter was very intentional. It's not only that I'm using this because this map is defined as a map from string to character, although, I mean, that is useful for retaining the same types all the way through the system. But the biggest reason I use it is because this return value can be null. And if I try and assign null to a char, then what's going to happen is, well, that's going to be converted to 0, or, well, it might not work at all, actually. I don't fully remember what will happen in Java if we do that. But we want null to be the value we get out so that we can explicitly check against it to make sure that the letter is non-null. And so I use character here instead of char. And okay, great. So if the letter is not null, then we know that we can actually use it. And, you know, that's fantastic. But not every character that we might decode is going to be valid for use. And the thing that might invalidate a character is if we've already used it. Now remember that every character in this string has to be unique. And we don't want to get all the way down to the base case before we determine whether or not a character is unique. That's a giant waste of everyone's time. It's a waste of computational resources. It makes the JVM sad. It makes me sad. So what we're going to do is use char's use to determine whether or not we can use this character. And so I'm going to add a criterion that in order to consider this character as valid, it cannot be used in char's used. And so the way I'm going to convert this character to an index into char's used is to grab Latin letter, the letter that we just decoded, and subtract a capital A. And so Morse map is always going to return capitalized letters. Morse code is just traditionally transliterated in all caps. And so we're going to stick with that tradition here and convert this letter, this code point, into a 0-based index into the Latin alphabet by subtracting an A. This is something that anyone who's done any type of string munging, maybe on a computer science assignment, or just because your job decided to make you munge strings, will definitely recognize. Great, so if we've used this, then the first thing we want to do is we want to actually indicate that we've used this character. right? So now we're in the point at which we're getting ready to make our recursive call, and so we've got to update the state of all of these different parameters to reflect the current state of the problem. So the first thing I'm going to do is I'm going to say, well, okay, so we've just determined we can use this character, and so I'm going to go ahead and mark it as used. And now what I'm going to do is here we're going to actually perform our recursion. Here we're going to say, do the recursion. And so this is the scary point of the problem, where we've got to think about how are we actually going to get to this next point. We've been talking about it this whole time, about how we want to use some characters from the Morse code string. But how are we going to actually apply this to get a string out? And so what I'm going to do is I'm going to store the return value. We always want to store the return value when we're doing recursion of this form, which you may recognize as recursive backtracking, where we're going to do something, try it out, evaluate if it worked. If it didn't, undo that and try the next thing. Standard recursive backtracking that we're doing here. And so we always want to store this value so that we can process it later. And so I'm going to make a recursive call, find alphabet. Now the Morse code string is going to stay the same. The Morse map is literally an immutable map. If you try and mutate it, it will yell at you. So we can't actually do anything with that. Now, here's a harder thing though. So the next index of the index of the next character that we want to consider will be the current Morse index plus the length of the character that we're currently working with. And hello, Expo Seed. How's it going? Hope everything's going well. Going good? All right. Awesome. Super glad to hear it. Glad to hear it. Glad to hear it. And so the character that we're going to consider next will be the Morse index plus the Morse length. And yeah. We're currently working on some problems. We're just doing essentially some fun practice problems with recursion. The big reason is just that recursion is one of these things that people always think is super scary and hard, and my goal here is to show everyone that recursion is not only really interesting and not necessarily as difficult as it may seem, but also something that we can have a lot of fun with to do some interesting tasks. So yeah, right now we're dealing with translating Morse code, and so that's kind of what we've got going on here. And yeah, it is fun. It's a super cool problem to consider, and it's actually fairly useful in terms of, you know, if you were a telegram operator back in the 1800s, put yourself in those shoes, this is something you would really like to have. So now I'm going to pass in the use characters, and now I need to have some way to indicate that I used that character, right? Remember that we were tracking the number of characters we used, so that we didn't have to loop through this Boolean array every time we hit a base case to determine if we used all the characters. And so I'm just going to pass in here num used plus 1 to indicate that we actually used a character. That's it. Okay, and so now that we have made our recursive call, that's the hard part over. We did the frightening part of the recursion. We did the actual recursion. Now let's see what we're going to do with that value that we got out. And so the thing about how we've written this method is that if we get a null back from our recursive call, then we know that the string that we're currently considering wasn't valid. That string didn't work. And so, you know, we've got to stop what we're doing and say, well, that option didn't work. We need to try something else. So I'm going to say, so if we got null back, then this letter didn't work. So we're going to say, so if decoded is null, then since that didn't work, we want to undo the work that we just did. And the only work that we really did here was setting chars used for the current character to true. And so to undo that work, I'm just going to set it back to false to say, well, that wasn't the best choice. Let's try again with a different length of character. However, if we got something back, then what we tried actually worked. That character that we decoded was a valid character. And so what I can do now is I'll say, so if we have a non-null character, then this decoding was valid. Yay, it actually worked. And so we're going to return the string we got back prepended with the Latin alphabet character that we decoded. And so if we got back a string containing, you know, ABC, and the current character that we decoded was D, then the new string that we're going to be returning is DABC, using D to indicate that that this character worked, and that was the character that we successfully decoded. And now this is really the core of the method. This is pretty much it. For the entire decoding, there's only one thing that will note that IntelliJ is yelling at us about missing return statement, and that it's one more thing we've got to consider when we're doing recursive backtracking is, well, what do we do if nothing works? Like, what happens if we just spun our wheels, we tried everything we could, and it all failed? What we usually want to do in that case is return our failure value. Our failure value for this method was null, so we say, we tried everything and didn't succeed. We're just going to return null. And succeed, of course, has two E's. And that's how we're going to indicate our failure. And so yeah, there is our recursive method. It's really pretty simple. All we're doing is we're just iterating through every possible character that we can get from a given index, trying to translate it into a Latin alphabet character, and moving on to see if that decoding was valid. And so now our next step is we've got to determine whether or not this actually works, right? We want to know if our code actually does what we think it will. And so what I've done to facilitate this is I've written a test harness using JUnit. JUnit is a Java unit testing framework that many of you may be familiar with. It's pretty much an industry standard way to test your code. And what I've done is I have written a test method that ingests a CSV file, which for us happens to be that CSV file that I was looking at earlier. It's going to ingest that CSV file and run this method, run the decode method, and ensure that the output that we got is equal to what we were expecting for every line in that CSV file, which is going to be a Morse code string. So yeah, it's called parameterized testing, where we essentially define a list of different parameters we want to run our tests with, write one method to run the test, and then we let the testing library handle the actual running of the tests. It's a super cool paradigm that I end up using a lot in my projects just to test different options, test edge cases, corner cases, all of that. And yeah, a great question. So, will you learn how to use JUnit in... And now people in the chat are mentioning 314. CS 314 is the introductory data structures course at UT Austin, University of Texas at Austin, which is where I'm a teaching assistant. And so the question is, so will you learn how to use JUnit in a data structures course? And usually the answer is no. Usually data structures and algorithms courses are concerned mostly with just the data structures and algorithms themselves, teaching you the theory and practice behind them. And things like proper unit testing and stuff like that are deferred towards software engineering courses, or courses that aim to teach you about the different tools that you may see in industry. And so yeah, so most schools will have a course. It's usually called software engineering or something like that. Some places call it development practices. That will teach you about unit testing and integration testing and continuous integration and all kinds of different tools that you may find useful. But yeah, data structures course, probably not something you're going to see, unfortunately. Although it is super useful, and JUnit is very easy to learn. I mean, I learned it in an afternoon, so, you know, you shouldn't struggle too bad here. And so looking at this test, just to run you through kind of how it works, I've declared that this test is parameterized, so it's going to take a number of parameters. I've declared that this test is going to have as its source a CSV file that is going to be sourced from the resources folder of my project. And it's going to be a file called compressed-morse-test.csv. And it's that one that I've been pulling up that contains all those Morse code strings. And then what I'm going to do is it's going to take in that Morse code string that we pulled from the CSV file, decode it using the method that we wrote, and then just print it to help us with debugging in case something goes wrong. Usually in unit tests, you might cut that out, but I've included it just for some interactivity. And then we're going to ensure that the Morse code string that we got in equals that Latin alphabet string translated back into Morse code. And now, this is kind of weird, but this is my workaround for the fact that Morse code transliterations may not be one-to-one. This is not a bijection. We may have a Morse code string that converts to multiple Latin alphabet strings, even though Latin alphabet to Morse code is a one-to-one mapping. And so the way that I handle that is just say, I'm going to translate the Latin alphabet string that you gave me back into Morse code, and then ensure that it equals the thing that we were passed in. And so that's just a kind of workaround for the fact that these aren't unique. And now that's enough kind of messing around. Let's see if this actually worked. And so now I'm going to use IntelliJ to run my unit test here, compressed Morse test. And if this works successfully, then we should have something a little over 1,000 tests passing. So yeah, let's do that. It's going to go ahead and build the code. Take a few minutes. And oh my, oh boy. That's not good. Okay, so, interesting. We passed 760 tests. That's, pretty good. We got, around a 75. But, oh boy, a lot of these failed. And they failed with a string index out of bounds exception. And, it gives me this kind of helpful warning that's saying, hey, you tried to compute a substring, this is from the substring method, beginning at character 79 and ending at character 83, but the string only had 82 characters, and so that was an invalid substring to try and fetch. And so now, the way to fix this is to go back to and see, okay, so this was thrown from find alphabet, line 29, and it was this called a substring, where we were fetching from the current index to Morse index plus Morse length. And now we've hit a really common source of error here, where we've attempted to grab a substring, and that substring ran off the end because we just didn't have enough characters to consider. And, that's pretty valid. So now what I've got to do is I have to have some way to indicate that I either want to run up to the maximum number of characters that I consider, or limit it. So I need to be able to limit the length to ensure that we don't run off the end of the string. And so the way that I'm going to do that is I am going to set my limit here. So we want to impose an upper bound of the end of the string. And so what I'm going to do is I'm going to say morselen is less than or equal to max blips, and Morse IDX plus morselen is less than the length of my Morse code string. And so this is just ensuring that we don't accidentally run off the edge. We're going to stop this loop once we have reached the end of the string. And actually, although I think I actually want to change this to less than or equal to, right, because this is an exclusive bound on the string. Right. And to anyone who's viewing who is a little bit confused by what's happened here, note that for loops, as with while loops and any other control flow structure in Java, can have compound conditionals. And so you can string together as many conditionals as you want here, and your loop will still work and stop once this entire condition becomes false. It's a useful tool to have. So let's run this again. Now, we've limited the length. Let's see if that solved our problem. Oh, looking good so far. Everything's running in lockstep. And we did it. All right. We passed 1005 of 1005 tests. I know that's a little bit hard to see currently, but we can see it up there, and we've got a little green check mark in our test output window to indicate that everything worked. So yeah, so that's great. Yeah, we have now successfully decoded Morse code into Latin alphabet characters. Awesome. Great. And so, just a reminder now that we've successfully done this, And now that we've got a whole implementation that we can look at, if you have any questions, you can always ask them in the chat. And note that questions actually extend past just questions about the code. You can talk about whatever you want. This isn't a Zoom meeting, so we can kind of just discuss whatever. We're just having fun here. But yeah, so yeah, here is our implementation, and I'll give everyone a second to kind of chew on that, and come up with any questions that you have, wondering why it works, why some things don't work, why we did something. Yeah, just feel free to type those over, and I will be sure to review. And I'll take this opportunity to get a drink of water so I don't go hoarse. All right, so not really seeing anything right now, so I'm going to go ahead and keep going, but again, if you have any questions, feel free to ask. So, now, here is a problem that I see. Now, if I click on the problems window, it doesn't really tell me that. It's going to yell at me about something in compressed Morse. Translator.entrySet is always empty. That's actually a bug in IntelliJ Static Analyzer, so I'm going to ignore that. Still chewing on it. Oh yeah, that's totally okay. If you need more time to chew on it, then, you know, you can absolutely do that. I'm going to try and keep this code on screen as much as possible so that you can review it. But anyway, so something that I see here, and I accidentally closed my test window, so I'm going to need to run this again, is if you look over to the right, it's a little bit hard to see, to be quite honest. Some of these tests took a while. This one took 30 milliseconds, and remember that these strings aren't very long. This one took 30 milliseconds, this one took 11 milliseconds. If we sort these by runtime, then you'll notice some of these took 127 milliseconds, 114? That seems really slow for a routine like this, right? I mean, these are short strings. If we feed it something even remotely larger, then it's just gonna balloon to some ridiculous size. And so, I want to see if there's a way that I can optimize this. And so in order to do that, we've got to go back to what we were talking about earlier, where when we're devising a recursive method, we have to consider, of course, our goal, right? Where are we trying to get? And we've got to consider, you know, how are we going to get there? What's a step that we can take? What's a recursive step that we can make to get ourselves a little bit closer to that goal? And that's how we get a recursive solution that works. Those two concerns work great if the only concern is I want it to run, and I want code that works, and I want to go home because this was tired and hurt my brain. And I'm tired and this hurt my brain. But if we are going to put on our high-performance programmer hat, which is something that I frequently do, that's the field that I work in, working in fintech, working on infrastructure projects, kind of lower level, close to the system, a concern is always how fast this runs. And to me, this is unacceptably slow. And so we're actually going to add a third question to our recursive problem evaluation. And that is not only what step can we make to get to our solution, but what step can we make to get there as quickly as possible? So what step, what choice could we make at any stage in the problem that would get us as close to our goal as we can? And now we stated that our goal here, our overall goal, is to use all of the characters in this string, in string Morse, to generate a permutation of the Latin alphabet. And so, if our goal is to use all of the characters, then the way we could get there as quickly as possible is to use as many characters as we can at a given time. And so yeah, so Sardite mentioned in the chat, try bigger Morse lengths first. And exactly, that is an optimization that we can make. Instead of starting off with the little tiny characters, what if we started with the longer ones instead? And so that's going to use up more potential options as we go down. If we were drawing a decision tree for this problem, the more characters we use, the fewer choices we have later on for potential string remainders. And so, yeah, so what we're going to do is we're going to start off with bigger Morse letter lengths first. And now this is a problem-solving approach that we call greedy problem-solving. And now in other fields, we might say that being greedy is a bad thing. If you're a business student, then you might say that being greedy is a wonderful thing. Greed is good, from Wolf of Wall Street? Is that what that's from? I don't know. I don't watch many movies. But yeah, greed is good. And in terms of writing recursive methods that we want to run fast, greed is very good. Greed is tantamount, or paramount. No, sorry, paramount, yes. And so what we're going to do is, to make this a greedy solution, we're going to start with longer letters first. And so now I'm going to change my loop. We're going to start at max blips. We're going to go down to 1, and so I'm just going to say Morse length is greater than 0, and we're going to decrement our length here. And now again, this seems like it would work. Logically, it makes sense. Instead of going up from 1 blip characters up to 4 length characters, we're instead going from 4 length characters down to 1 length, or 1 blip characters. But we're gonna run into a problem here. We're gonna run into a problem, and it's, believe it or not, it's that same problem that we had earlier. Morse length can run off the end of the string. And so we're gonna have to limit this one too. So we're going to have to limit the starting point now instead of the end point. Yeah, as ExpoSeed said in the chat, great observation. Yeah, Morse length plus Morse index is going to be too long. We're going to get that same string index out of bounds exception that we got earlier. And I don't like getting exceptions. The IntelliJ default exception color is a red that doesn't stand out well from my background, so it's hard to see, and also it means that I have to keep working to solve the problem. And so what I'm going to do is avoid the exception altogether, since we've already spotted it, by setting the starting point to not Minguo chronology. We're not using the traditional, is that the traditional Chinese calendar? I think it is. Oh, we're going to start off with, sorry, math dot the minimum of the maximum length and the most characters that we can possibly use is the length of our Morse code string minus the Morse index, right? This is just essentially how many characters we have left. And to make this a little bit clearer, I could extract this into a variable. Int chars left will be that. Okay, great. And so now here's a greedy solution to this problem. We're considering the thing that gets us closest to the solution first, and then going down to slightly less optimal choices from there. Now, our previous solution ran in a total of about 3.5 seconds. We had some tests that peaked all the way up to over 100 milliseconds. Let's see what happens when we run our greedy solution. All right, running our tests. You know, this seems a little bit faster. 3 seconds, 41 milliseconds. That was a little bit better. And now you'll see that some of these are still taking a pretty long time. But on average, we've got something that runs a lot faster. We now have a lot more 1 or 0 millisecond tests than we did prior. And so here we know that our greedy solution worked, right? The greedy solution that we tried using more characters first was a success. We got to a solution faster. And now we've got a solution to our recursive problem that not only works, but it also works pretty fast. And for the majority of our strings, works so quickly that JUnit didn't output a runtime and output 0 milliseconds. And so yeah, so there we go. That's that. That is our Morse code problem. All right, yeah, in the chat, yeah, we did it. Awesome, yeah, correct, yeah. So that is our compressed Morse code problem. All done. Anyone with any, we did it in no milliseconds. Yes, we did, ExpoSeed. Yeah, we did it in no milliseconds. Writing the solution, unfortunately, takes a little bit longer than no milliseconds. But, you know, we got there in the end. And yeah, one shot, no kill. Greed is the answer. Yes. With recursion and recursion that we want to run quickly, oftentimes, greed is the best thing that we can do. Alrighty. And so yeah, that is the end of that problem. If you have any questions on what we just did, then again, feel free to post them in the chat. What about microseconds? You know, I don't know if JUnit outputs microseconds in the runtime. I think it only outputs milliseconds. I mean, it's going to take some milliseconds to run, right? It's always going to take some milliseconds to run. Or some microseconds to run, just because computers are not magic and cannot immediately output an answer. It'd be nice if they could. But yeah, we do have at least a little bit of latency, even if it's only a few nanoseconds. Everything we do is going to take some time. So yeah, we're not going to be able to get it down to no time at all, unless we do nothing, of course. And XOC, there's no way to optimize it further. Now, there is a way to optimize this farther. And we could do it, but I'm not going to because it would take us pretty out of scope for what we want to do today. But we can actually optimize this a little bit further using a technique known as dynamic programming. So dynamic programming is essentially a programming technique that involves us performing partial computations, storing the results of those computations, and if we ever try and perform the same computation again later, then we just retrieve the value from the previous computation instead of continuing on and running the same thing again that we've already done. And so it's a way to reduce work. And now DP, as it's often called, dynamic programming, is, as Exposeed says, it's super cool. It's a great way to improve the performance of your program with some trade-offs. The biggest trade-off of dynamic programming is memory. So we actually have to have somewhere to store all of those partial results. And oftentimes that involves just consuming scary amounts of memory. Yeah, space, exactly, yeah. It's a time-space trade-off. And so our runtime is faster, but the space requirements could potentially balloon pretty high. There is also another issue with dynamic programming. There's another trade-off. And that is that dynamic programming is really hard. Lots of people struggle a lot with dynamic programming. Dynamic programming is one of the most difficult things that, as programmers, I think we have to learn. And as software engineers, you may occasionally have to interact with, because the solutions are often non-intuitive. They require a lot of thought, they require a lot of planning, they require a lot of analysis of your problem to ensure that the duplicate work that you're doing, or that you're avoiding, is actually going to return the right result. And so yeah, so DP is wonderful for certain problems, and we're actually going to do a little bit of DP later. But right now, we're not going to be doing that. Oh, and from the chat, store every possible Morse code and simply write code to access that. Okay, we could. Yeah, we could do that. We could literally generate, I guess what you're saying is generate every permutation of the Latin alphabet and then, translate it to Morse code and see if it matches. We could do that. However, that's actually probably going to be a lot slower than what we have right now. Because you're going to have more options, right? You're going to have, if you're using every character uniquely, then you're going to have 26 factorial different strings, which converts to, oh boy, I don't even know what that converts to. It's going to be some giant number. But here, we'll pull up a calculator to look at it. And the calculator, in all of its infinite wisdom, decides that it doesn't want to re-render. So it's going to be, let's see here, yeah, 26 factorial. Yeah, you know, to be quite honest, I have 32 gigs of RAM. I don't think I can store that many strings of length 26, right? So that's going to be times, 26. Yeah, times 26 letters, right? And so that's just the different number of characters that we have. And so we're going to have 10,000 million, billion, trillion, quadrillion, quintillion, tillion. Yeah, 10 octillion characters that we have to store in memory, and I know that I can't really store that. So yeah, that solution unfortunately wouldn't quite work. And is there a course in dynamic programming? Most schools will have a course that actually covers dynamic programming. A lot of data structures and algorithms courses especially will talk about dynamic programming. If you're in my course, CS314, then we're actually going to talk about it a little tiny bit later in the semester, and then when you move on to the dedicated algorithms course, you're going to talk about it a lot. By the end of that course, there will be two outcomes. Either you will be really good at dynamic programming, or you will decide that you want to avoid domains in which dynamic programming exists. And so yeah, so you're going to get a lot of experience with it later. And we're going to do some DP in a little bit, but I'm not going to do that for this problem. Also, looking at this more, thinking about this more as we've been chatting, I don't think dynamic programming is actually going to be useful for this problem. Because the thing is, I could store the characters that I've generated from a given index, right? The Latin alphabet characters that comprise a string starting at the given index. But remember that there are actually multiple ways to decode a string depending on which characters we've used so far. And so, you know, I'm not really sure that a DP solution would be A, more efficient, or B, even remotely space efficient. And so, yeah, we're just going to keep the simple recursive solution for now. And if you want to see some DP, we're going to get to the next problem. And actually, now that we've spent a lot of time on this Morse code, I think everyone's now at least fairly comfortable with the type of recursion that we're going to be working with today, primarily recursive backtracking. Let's go ahead and move on to our next problem, which I think is actually even more interesting. And even more of kind of a fun programming challenge. So yeah, let's move on to the next one. All our tests pass. Let's move on to this next one here. So this problem is called word funnel. So word funnels it's a game that some people actually play by hand. And honestly, I'm not sure how well I would do at this game by hand. I think that I have a pretty big vocabulary, but it seems really, really hard. Where essentially, if you're given a string, then you try and figure out the longest chain of words you can that you can form from this word, where each subsequent word in the string is the same as the previous one with one character removed. And so the example we have here is Nash, G-N-A-S-H, goes to Gash, removing the N, goes to Ash, removing the G, goes to Aw, removing the S. And so that's what we're going to be working with today. And I'll note that this is one of those things that actually seems really trivial, at least in my opinion. Like, if you're given this problem and you're like, how would I solve this? You're kind of like, well, wait a second. This actually seems pretty simple, right? All we've got to do is loop through a dictionary. But then you remember that dictionaries are giant. This is the dictionary that I'm going to be using for this one. This dictionary contains 172,823 words. And so if at every point we just try and loop through every string and determine one that is going to work as a successor to the previous one, we're going to be here for several years. And probably also run out of memory and lots of other stuff. So we're going to implement a more optimal solution to the word funnel problem today. Now, something else that's kind of fun about this problem is that storing that giant dictionary in a Java set uses a ton of memory. We've got to have an entry in the set per word. And so, you know, yeah, just using a standard Java set, using a tree set or a hash set is going to be too inefficient. Accesses to it are going to be pretty slow. I don't like that. So what I actually went and did is I wrote my own set of strings. I wrote my own set of strings in this class called Compact Lexicon. Now, Compact Lexicon implements what is, to be honest, my absolute favorite data structure on the planet. It's a data structure called a compact directed acyclic word graph. And you're like, what on earth are those means? And if you want to get an even more technical title, it's a deterministic acyclic finite state automaton for string segmentation. And so yeah, so there's a whole bunch of scary computer science theory words, but what the... Yeah, and it's super long. It takes a long time to say, as General X Red said in the chat. Yeah. But what does that mean? So what this means is that we're going to take a string. We're going to take a string. And actually, let me see if I can get a visual aid for this. Let me pull up a diagram of one of these things. Let's see here. Directed... Give me 1 sec, acyclic word graph. Let's see here. Ideally, I just have the diagram from the paper that I read, but it looks like I'm not going to be able to get that without logging into JSTOR, which I really don't want to do. So here, this works, actually. This will work. Here, from our friends at ResearchGate. And so this is a rendering of a directed acyclic word graph. And so here... over on the left, we've got a data structure called a trie. Tries are something that you'll often also learn about in data structures courses. If you're in my course, then you're going to learn about it at the end of the semester. What a trie is it's basically a tree where each edge corresponds to a letter. And so, for example, if we had a string, let's say that we had the string dance, and we wanted to see if that was in this try. What we would do is we would navigate down the different branches of the try, seeing if there's a potential branch, if there's a potential edge between two nodes, that was the character that we were looking for. Each edge corresponds to a single letter in a word. And so this try contains 4 strings. It contains dances following this path, or dance following that path. It contains darts following that path. It contains start following that path. And it contains smart following that path. And hey, that's kind of cool. That's an interesting structure, but it's kind of inefficient. And if you look at this, then you'll see exactly why. We have some repetitions in this try, right? Art, the T repeats. And so what we want to do is we want to turn this try into a maximally compact version of itself, so that we're combining not only common prefixes, as we do here, but also common suffixes. And so this here is a directed acyclic word graph for these same words. And so you'll see that what happens is it starts off a lot like a try, right? In that we still are going to be navigating down these different nodes with edges, but suffixes, like the art on start and smart, are combined into a single branch of the try. And so yeah, so tries are not like trees. Trees only split. Tries can actually directed acyclic word graph, can actually come back into the same branches. And so it's not really like a tree. It's more like if you've ever seen a railroad junction. This actually might be something that people haven't seen. So let's pull up a photo of a railroad junction. Yeah, here we go. Here's a railroad junction. So you can see that we've got all of these different, this is going to the City Skyline subreddit for some reason. That's not really what I wanted. But anyway, so here we've got all of these different paths that split, but some of them also merge later. And so that's kind of a good analogy for a directed acyclic word graph. And General Xred asked the question in the chat of, it's the edges that store the letters and not the nodes themselves. Well, we'll get there. So with a try, you can represent it either way. Each node can contain a letter, or each edge can contain a letter. I personally like the node approach because I have to have nodes anyway, and it prevents me from having to write a separate edge class. And now, the way that you construct one of these things is complicated. This class is 586 lines long to implement the algorithm for constructing a directed acyclic word graph for a list of strings. And actually, mine is a little bit fancy because I did some very, very basic theory, which is something that I always try and avoid. I'm not a computer science theorist, not a theoretical computer scientist, not a CS grad student, more of a software engineer. But, you know, I went ahead and decided that I would put on my theoretician hat for a few minutes and figure out if I could make this tree use fewer nodes. Because the problem with this is that each letter in the initial algorithm, each letter would still need its own node, and that seems really inefficient. And so what I did is I changed it to come up with a new data structure that I call a compact directed acyclic word graph, which is where if we have several nodes in a row, each of which only has a single edge pointing to it, we combine those into a single node. And so you can actually have multiple letters in a node instead of just a single letter for each. And this improves memory usage. It also actually improves runtime a little bit for accessing these. And so yeah, so that's what we've got here. That's what compact lexicon is. It's really, its external interface is no different from a normal set of strings, but it's actually working with this compact directed acyclic word graph in the background. It's a cool aside, a very fun data structure. If you want to know more about it, then like totally ask in the chat. I love talking about these things. They're so cool. But anyway, let's move on to the actual problem. And so the problem that we're doing here is we're trying to come up with a word funnel given a certain word. And now, what we want to do here is we want to figure out what is a word funnel that we can make from this string given a certain lexicon, right? And so that's going to be our compact lexicon. It's just a set of the potential words that we could have in the funnel. And now, this problem is really interesting because, as I mentioned earlier, it requires dynamic programming to get an efficient solution. It requires DP to get an efficient solution because of the size of this lexicon, right? Again, the directed acyclic word graph, I need to come up with a better name for those. If you have any ideas for a better name for these things, please type them in the chat. This is getting too wordy, but anyway, the compact directed acyclic word graph is going to be this set. You know, it's pretty fast. Operations on it are fast, but still iterating through the whole thing constantly is still going to be slow no matter how we cut it. And so what I want to do is avoid repeating possible options. And we're going to get there in just a second. But let's go ahead and just start this method. And so what I want to do is I want to... Oh, taking the acronym, so directed acyclic word graph is DOG. And yeah, that's actually, yeah, Expo Seed and Prithvi J. Yeah, that's something that actually shows up in the literature. Some people do call it a dog. I mean, if I wanted to give it a more, you know, a friendly name for the compact version, then I just call it a sea dog. Which I've actually Googled in the past and is apparently the name of a character from some podcast. But honestly, that seems kind of lame. Like, I want like a short, like punchy name, like Try or Deck or something like that. I've considered just calling them lexicons, or in Greek, I guess the plural of lexicon would be lexica. But you know, that's kind of lame. It already refers to something. We need some like fancy CS word that you have to Google when you see it. Anyway, let's go ahead and move on to this problem. And so in this problem, just like the last one, we're going to start off by evaluating our problem constraints. Our problem constraints are, we have a starting string, right? So the string that starts the word funnel is something we definitely need. And of course, we need our set of candidate words. And that's all fairly straightforward. However, in this problem, it's going to get a little more complicated. It's going to get a little more complicated because I don't want to have to iterate through every word every time I'm trying to find a successor to a given word. A successor just being a word that has one character fewer than the previous one. And so what I want to do is I want to store the successor to each string that generates the longest word funnel. And this part here is where the dynamic programming comes in. We've got a few questions in chat. Popcorn too hot, no Emacs today. Yeah, unfortunately no Emacs today. My Emacs setup for Java isn't great. And also I really just kind of wanted autocomplete and all of that for this. I can get that in Emacs, but it's kind of slow. It's not as good. And we're also working with JUnit and a few other libraries that would normally require complicated build tools to use, but using IntelliJ, I can avoid having to set up a Maven or Gradle project to actually run the tests. And so yeah, that's why we're using IntelliJ. Partially just because I'm lazy, partially because it really just is going to make life a lot easier for us here. Yeah, the IntelliJ for today. IntelliJ for today. And yeah, Gradle and Maven is bleh. Yeah, Gradle and Maven are bleh. I've used both. Maven hurts me because of XML. I don't like XML, and I think that its dialect of XML is kind of horrifying. I've played around with writing a dialect of YAML that will convert to Gradle XML, to Maven XML, but at that point, I'd honestly rather just write my own build tool. And Gradle I've only used for Kotlin. It seems to be a little bit more reasonable, or maybe IntelliJ just has better support for it. But yeah, the Java build tools are crazy. They're insane. They're honestly not very good. Oh, we had a suggestion from General X Red in the chat for a name for our data structure as Condog. Oh, like corn dog. I like that. I like that actually. Yeah, or for compact, I could call it a calm dog. Yeah, maybe. And yeah, Exoseed, Kotlin is JetBrains' baby, so they put a lot of work towards it. They do, yeah. Kotlin integration in IntelliJ is really good. I've been super impressed by it. I'm still kind of learning the language. I haven't done any super big stuff in it. Maybe at some point we'll do a Kotlin stream, and so you can kind of see what that looks like. It is an interesting language, and they definitely have really good support for it in IntelliJ, but as someone who's done a lot of functional programming in languages like OCaml and Lisp, and even a little bit of Haskell when I hate myself a sufficient amount to do that, Kotlin seems like weirdly limited. Like, I keep trying to do things that I think should definitely work in a language that provides the abstractions that it does. And they just don't, because the language has some weird limitations, I think, to keep it more similar to Java. And so, yeah, it's kind of a weird uncanny valley between, like, Java-style, super wordy, super explicit OOP, and the kind of, like, slight magic that you get out of the compilers of a lot of functional languages. But maybe it's just because I'm learning it. I'm going to keep working with it. Maybe I will be more comfortable with it at the end, and those kind of weird concerns will go away. But for now, yeah, for now we're just going to be sticking with Java, I think. Although, if you ever want me to do a stream in another language, then you can tell me to do that. We could do an OCaml one at some point. That would be fun. But anyway, moving on to the word funnel finding. So yeah, so DP, dynamic programming. Store the successor to each string that generates the longest word funnel so that we don't have to re-find the successor for each word. That's kind of an interesting problem, and so we need to figure out, how am I going to do that? Like, how am I going to actually store the successors? And now, the way that I would kind of like to do that, starting off, is I'd like to use some type of map, right? We're mapping strings to strings. String to string mapping, we're usually going to reach for a map. And so, yeah, and so we'll probably end up using a map here. And because I don't care whether or not these are sorted, I'm not ever going to be printing the map or iterating through it. I'm just going to be using it as, essentially, as a cache, as a cache to just store some values and retrieve them later. I'm going to use a hash map, I think. Yeah, so we're going to use a hash map of string to string. And I'll just call it successors. And we're just going to start off with a new hash map. Lovely. Great. General X read the chat. Stream another language. Stream while speaking in Latin. Posso fluenter loqui latine, sed non in interreto. Ite vero. Et non programmens. Yeah, so maybe not Latin. Although we certainly can. And yeah, I can kind of speak in Latin. My spoken Latin isn't fantastic, but I'm at least decent at it. Did I just summon a demon? No, I did not summon a demon. I know that the background music that just started probably doesn't make you think that I didn't either. But no, what I said is I can speak in Latin reasonably fluently, but maybe not on the internet. And I said certainly not while programming, because yeah, I'm not really sure actually how to refer to almost any, like, computational terms in Latin. The closest thing to a computer the Romans had was maybe an abacus. The Greeks had the Antikythera mechanism, which was cool. But they, as far as we can tell, we don't know how they used it. And yeah, the Romans honestly weren't super interested in computation anyway. Illuminati confirmed. Yeah, maybe. I mean, if anything, I'm not sure the Illuminati really worked in Latin. Maybe, like, I don't know, Catholic Church confirmed. But not, honestly, no. Abacus stream. Yeah, sure. At some point, we will pull up, yeah, me just using an abacus. I'm not very good with an abacus. Like, I've seen those videos of students in Japan who, like, who start off with an abacus to learn, like, mental computation, and then get to the point that they don't even need the abacus because they can just visualize it and do these, like, insanely complicated math problems really fast by just kind of, like, flicking their fingers on an abacus. To me, that is absolute magic. I'm not very good at it. The most I can do is addition and subtraction. Even multiplication on an abacus is not something that I really want to subject myself to. Just a little beyond my pay grade. I like calculators. I really like calculators. I really like the best calculator of all, which is just Python. You can just, type stuff in, get an answer super fast, you get math functions, all that good stuff. But yeah, so yeah, maybe at some point. Anyway, so yeah, so here we've got our map of string to string, where the key is going to be the string, and the value is going to be the best successor for that string. Oh, and there we go. Popcorn Too Hot's got a clip for us of the Latin in case anyone missed that and really wants to listen to it. Anyway, so yeah, so here's our successors map, and what I'm going to do is I'm going to now pass this onto a method that's not actually going to really be solving the problem. It's going to be doing pre-processing for the problem. And so what it's going to do is it's going to find the best successor for every word. So the successor that generates the longest word funnel. But what it's actually not going to do is find a word funnel. The word funnel part is actually going to be mostly ignored for right now. And that's kind of weird, but you'll see what we're going to do with this later. And it's very interesting. So yeah, so what we're going to do is we're going to start off by just finding the best successor for every word. And so I'm going to write a method, private, static, and, you know, in terms of what we actually want to return here. So this is an optimization problem. We're trying to find essentially the best possible successor, the successor that generates the longest word funnel. And so given that we are defining our measure of success as length of funnel, I'm going to return funnel lengths generated by a word. And that's going to be how we structure this, just so that we can immediately know, what funnel did, or not what funnel we generated, but how long was the funnel that we generated. And so we can go ahead and do that. And actually a fun side effect of this is that if you just want to know how long the longest funnel is after calling this method, because of the way we've defined our recurrence, this method will actually return the longest funnel for the first word you pass in. And so yeah, that's cool. If that were the problem, we could solve it super easily. And actually, this daily programmer problem that I got this from only asked people to find the length of the funnel, which is a little bit easier. But, we're capable here. You've sat through an hour and a half of me talking about recursion. So clearly everyone's pretty mentally nimble, everyone's big brain, so we're going to go ahead and just get right to finding the actual words. So what I'm going to do is I'm going to write a method called find successors. Or just find successor for a word. I'm going to pass in, let's see, what do I want to pass in? I want to pass in the word that we're actually going to be considering, the word we're trying to find a successor for. I'm going to need to pass in my words, right? And so I'm going to need to pass in that set of strings, my lexicon. Lexicon just being a word for basically a list of words in a language. Linguists will also use the term vocabulary, but I think lexicon sounds cooler. A map, so that's going to be our map of string to string. Map of string to string, which I will call successors. And, oh no, we have a warning. What is this? Oh yeah, I just got to import map. Cool. Okay, all good. All right. So now let's figure out how on earth are we going to do this? So what I need is I need to be able to determine the best successor for each word. And the way that I'm going to do that is by figuring out the length of the word funnel generated after that successor. But, I'm thinking about this now, and it's all well and good to have a string that does this, right? So to have an actual string that's just the successor, and then if we wanted to figure out the length of the funnel after that string, then all we would have to do, pretty simply, is to iterate through the map, constantly getting the successor for that word, and, just walking the chain, basically, just walking down the map until we reach the point at which we have found that the length of the funnel for that word. And, I like that approach. That seems like a good initial approach, and so what I'm going to do is I'm going to write another method called funnel length. And what this method is going to do is given a word, so string starting word, and the map of successors, I'm going to compute as an integer the length of the funnel that's generated starting at that word. Okay, great. So that's our current objective. And so let's go ahead and do that. And so now what I need to do is I need to figure out the length of the funnel. And what I'm going to do is I'm going to say, okay, so int funnel length. And now every word funnel, I will note, has at least one word, right? It has at least the starting word. We can't make a funnel that has 0 words unless we start with, well, unless we don't have a starting word. But we've got to have a starting word. So the funnel length is always going to start with 1. And now I've made a bit of a faux pas here. I've named a variable the same thing as my method. That isn't something that I really like doing, and so I'm just going to call this length. And the reason I don't like doing that is that it can kind of blur the line between variables and methods. And even though Java is a language that has separate namespaces for both of them, I think it makes the code hard to read, especially once we start dealing with function references and things like that. So yeah, you know what we're going to do? We're just going to say, we're going to start off with a length of 1. And my word here is starting word. So what I'm going to do is I'm going to say, so let's see here. So what I really want to do is I want to keep going through this map until I find a word for which there is no successor. Just want to find a word for which there is no successor. And so what I'm going to do is I'm going to say, okay, so string successor equals successors dot get starting word. Okay, and now remembering the map get method, if we have a successor in the map, then we're going to get a string out. However, if we don't have a successor, then this is actually just going to return null. And so the way that we're going to find the length of the funnel and say, so if the successor is null, we're going to return, well, we're going to return 0. We're going to return 0. Actually, I don't need this length variable because what I'm going to do is write this as a recursive method. And so yeah, so here's a little scary. We're now writing a recursive method inside of a recursive method. We are nesting recursion, which is always a bit frightening. But the reason I'm doing this is to show you something that I think is super cool. And this actually isn't something that I was planning on doing. Just as a full disclaimer, I didn't really do these problems before going on stream. I mean, I did think about the problems a little bit. I had to type up the descriptions, but I haven't really written full solutions to them. And so I've realized that we can do something kind of cool here, which is I can return, in this case, 1 plus the length of the successor of the successor. And so, yeah, so this is kind of crazy, actually, right? So now we've said, okay, so we're going to grab the successor. If there's no successor, I'm going to return 1. But otherwise, I'm going to return 1 plus the length of the funnel that originates at the successor. And so, yeah, so here we've got recursion inside recursion. Absolute madness. And actually, I think I want to return 1 here because, you know, we do always want there to be at least 1 word in the funnel. But more specifically, this is a special type of recursion called tail recursion. And so what tail recursion is it's a form of recursion in which the last operation that is always performed is a recursive call. And so here, this is tail recursive because we're adding 1 to the length of the funnel. And now this is not true tail recursion, actually. True tail recursion would require us to pass an additional variable for the length of the funnel and return that. But it's very close to a tail recursive solution, where we're essentially saying that we're going to take a single step at a time and then call the next method to find the funnel of the step that we took, of the successor. Which, to me at least, is very elegant, very nice looking. It's just a super clean way to do this. And so now that I've waxed poetic about that, what I want to do is I am now going to do my little bit of dynamic programming. I'm going to say, so if I have a successor, so if successors dot contains key, the word that I'm currently considering, what I want to do is I don't want to actually go through. Yeah, and Expo, you're completely correct. The last thing that would happen is actually the addition operation, and that's why I said this isn't pure tail recursion. If we wanted to do this tail recursively, and I mean I can, it's not that hard. We need an accumulator variable, And what we would do is, we would, every time we do this, we would say, okay, so if the successor is null, instead of returning 1, we would return the accumulator. And then here we would call funnel length with the accumulator value plus 1. And so this is how tail recursion normally works, in that we have to store a running value that we modify as we move on to each step. And so this is now fully tail recursive. The last operation we perform is the method call, and we modify the accumulator to get the length. It's a little bit out of scope, but yeah, this is a pattern that you see a lot when you're working with tail recursion. It's kind of cool. It's something that I do a lot when working in languages that support something called tail call optimization, which is where if you have a tail recursive method, the compiler converts it to a loop. And so it runs super fast without the overhead of recursion. And so you can write your algorithm in an elegant recursive way, but still have all the performance benefits of a loop. Java's compiler, the current Java compiler, and current JVM, unfortunately, do not support full tail call optimization. However, there is a project in the works. What is it called? This is gonna bother me now. Let me look it up real quick. Java tail recursion. Oh, what's it called? It is project. What is it? Well, I can't find it right now, but anyway, if anyone knows, totally type it in the chat for the kind of like ongoing Java project to make it work a little bit better with recursion like this. But yeah, and so yeah, so tail recursion, tail call optimization is super cool. The F# compiler can do it. F# is a language I've worked with a lot. OCaml's compiler, Haskell compiler, it's trivial that they can do it. Yeah, and another benefit of tail recursion is you're not going to ever get a stack overflow because it's just a loop. And so if you write a tail recursive method and your compiler has tail call optimization, this method could be guaranteed to never give you a stack overflow. Oh yeah, Expo-C, that's correct. Yeah, exactly. Project Loom. Yeah, thank you for that. Yeah, Project Loom. That's the project that they're doing two things. They're trying to implement lightweight multi-threading into the JVM, in addition to doing things like tail call optimization. Yeah, thank you for that name. That is completely correct. Yeah, Project Loom. And so if this were running on the Project Loom JVM and compiler, we would never get a stack overflow due to tail call optimization. Yeah, which is super cool. Thank you for posting that. But anyway, here's our DP part. If we've already found the successor for a word, I don't need to recompute its successor. We already found it. And so what I'm going to do is I'm going to return the funnel length of that word. And we'll pass successors. And now my accumulator is going to start at 1, right? Because every funnel is going to have at least one word in it. So yeah, so this is a way now that we have now said that we are going to avoid recomputing the successors of words whose maximum successors we already found. We're just going to retrieve it from the map, navigate down the funnel, return the funnel length. Yeah, so now that we've done that, so this is our base case. It's also our DP for this problem. Now we've got to move on to the recursive case. Oh, I should set my game as science and technology. That's actually a good point. Let me figure out how to do that. Category, science and technology. Okay, cool. Okay, nice. Yeah, thank you for that, Popcorn Too Hot. This is my first stream, so I'm actually not super... I'm not actually super well versed with how all this stuff works. So yeah, thank you for telling me that. Went ahead and did that. All right, great. Maybe we'll get a few more people in here. And yeah, so now we've got our recursive case. And now our recursive case is we want to find the longest possible successor of this word. And so there's our goal. We want to find the longest possible successor for this current word. And so let's see here. So what I'm going to do is I'm going to need a few things. I'm going to need to store the length of the longest funnel, right? The word that generated the longest funnel. I need to know how long that funnel is so that I can actually perform our optimization. So I can actually determine, you know, how long was that funnel, and is that funnel better than another one that we have computed. I'm also probably going to want the string that served as the best successor here. I'm going to need to know which string worked the best. And so, now that I've got that, and actually, yeah, I'm just going to set it to null. Why not? Although actually, no, I'm going to set this to an empty string. And here's why. So, one option that I have now at this point, our recursive case, where we're trying to consider every word that we can, is that I could loop through every single word in the lexicon, right? This is a set, it's iterable. Loop through every single word in the lexicon. And just determine, you know, is that word a successor? If it is, then recurse with that word and see if we can generate a longer funnel. But the thing about that is, like I mentioned earlier, that's super slow, right? That's considering a ton of options for our dictionary called Enable1 that we're using. I mean, that's, what is that? That's, you know, our 127,000 or so words on every single recursive call. That's just atrocious, right? That's going to balloon our runtime to some ungodly level. So what I'm going to do instead is, instead of trying to determine whether each word is a successor, I'm going to generate each possible successor and determine if that successor is an actual word. And so what I'm going to do is, if my word is Nash, then I'm going to start off by, let's say I'm going to start off by removing the G and generate Nash. I'm going to then go ahead and remove the N and generate Gash. I'm then going to generate GNSH, removing the A, and so on and so forth. And so that's what we're going to do here. Because the number of choices that I have to consider if I do this is only the length of the string. Right, and we're, to be quite honest here, probably never going to have a string that's actually 127,000 characters long that we're trying to find a word funnel for. And so, this is a way more efficient solution. And so, let's go ahead and do it. So, I'm going to say I'm going to loop through my string. So I'm going to loop from index 0 up to the last index of the string. So I equals 0, I is less than the length of the word. We'll increment every time. And I here isn't named too well. I is actually going to be the character I'm going to remove. And so actually I'm going to go ahead and rename this to, let's just call it remove index. There we go. Just something to make it a little bit more clear what that index is doing here. Okay, great. And so now what I want to do is I want to generate the actual successor word with that character removed. And so let's think about how I'm going to do that. And so I'm going to say string successor. And now what I'm going to need to do here, very likely the best way to do this, because Java strings are immutable, I unfortunately can't just say prevword dot remove. Right? There's no method that's just going to let me straight up remove a character from a string. Java strings are immutable. And so what I'm very likely going to have to do here as I scroll through this, actually just to make sure that I'm right, and that I don't have to write my own character remove. No, okay, I do. I do have to remove my own character remove method, or write my own character remove method. Is I'm going to use two substrings. I'm going to concatenate the substring before the index to remove with the substring after the index to remove. So that's pretty simple. I'm just gonna say previous word dot substring from 0 up to the remove index. And now this behavior of substring and that the endpoint is exclusive is super helpful to me because I don't have to do any math with the index to remove. Great, lovely. And to that, I'm going to add prevword.substring from 1 past the remove index up to the length of the word. Oh, and I'm getting a warning saying that, oh yeah, right, by default, substring will go to the end of the word. So I actually can just do that to get the substring. And so what we're doing is we're going to say, so if my word, again, just as an example, is Nash, and I'm removing, let's see here, index 2. Then it's going to generate a substring from index 0 inclusive to 2 exclusive, and then generate from 3 inclusive, right, 2 plus 1, to the end of the string. And that's how we get our output. So there's our successor word. And so now what I need to do is, now that I've got a successor, I need to determine, is it an actual word? We're going to generate lots of nonsense here. And, you know, we don't want to permit nonsense. And so what I'm going to do is say, I need to determine whether or not this word is in my lexicon. And Expo Seed's got a question in the chat. Would this have the same issue as before of going off the end of the string? Yeah, right. So in the previous problem that we did, the compressed Morse problem, we ran into this problem where we were taking substrings that were running off the end of the string. And in this case, that's not actually going to happen because of 2 things. The first one is that the remove index is always going to be less than the length of the word, right? And so here we've bounded this, so we know that remove index is never going to be off the end of our word, and so that's always going to be a valid index. We've also got the fact that substring, if you pass it a count, or I'm sorry, an index equal to the size of the string you want to take a substring of as the starting point, then it returns an empty string. And so yeah, so we're not actually going to have that case because of the way that we've structured our loop with the substring calls. But it's always a great concern to have. It's definitely something that we want to keep in mind as we go, but thankfully, we're not going to hit that here. And yeah, I think that is neat. I think that is neat, Expo Seed. I think that's pretty cool. I think that's pretty cool. So what I want to do is I want to determine, is my successor a word? And remember that lexicon, very thankfully, is a set. All I have to do is I say, so if the lexicon contains this word, then we want to continue. And now, anytime I start calling .contains on a data structure, you might get a little bit nervous, because you're like, wait a second, these operations are often slow. If this is a linked list or an array-based list, it's order n. If it's a trie, then, I mean, it's order n for the length of the string. For our compact-directed acyclic word graph, or as someone earlier suggested, we call it a corn dog, then what we're going to end up with is a runtime for this that's roughly order n, but where n is the unique number of segments in the word. And so it's actually going to be a little bit faster than the uncompressed word graph. So yeah, so this contains call isn't too concerning. Order n, where n is the length of the string we're looking for, which, compared to the size of the data structure, is nothing. So this call is honestly pretty safe to make. And that's part of the reason why I wrote this as a compact-directed acyclic word graph, because they're super duper fast. Anyway, now we've determined, so if this is actually a word, then what I want to do is I want to determine the length of the word funnel generated after the successor. So I'm going to say, so next length is going to equal 1 plus, right, 1 to represent the current character, plus, and now this will be a call to find successor. The word that we want to find the successor for now is the successor that we generated. Lexicon is immutable. And successors is just going to be the same map. And now at this point, an alarm bell may be going off in your head, or at least it's going off in mine, and I'm glad that I remembered to do this before I ran the code and wondered why it didn't work. I haven't changed the successor yet, and so this is actually never quite going to work. It's never actually going to succeed, and so we're always going to be recursing. We will get there. We'll get there. We've just got to get a little bit further before we do that. And so now what I want to do is, so now that I've got a successor, find the successor's funnel length and determine if this is the new best successor, meaning that its funnel length is greater than, ooh, didn't mean to do that. Sorry, that's called next length, is greater than the maximum that we have, then we're going to store this as our best successor. So I'm going to say, so the new max funnel length will be the next length. And our best word is going to be the successor here. Okay. All right, great. And so, yeah, so here's kind of, I guess, the core of our recursion. That now what we're doing is we're looping through all of the different possible successors, figuring out the funnel length for each eligible successor, and then determining if that's the new best successor, setting the maximum length. And I'm going over this in my head as I'm talking, making sure that that's right, and it is. As I'm looking at this, it actually seems like an algorithm very similar to this would be what one would want to do in order to compute, like, succession for royal families. So, like, if someone wanted to know how many degrees separated from Queen Elizabeth they are, then they could run this algorithm on a tree that contains basically their family tree, and it would tell them. Or actually, no, I'm sorry. It would be, you would use this to determine, how many people, like, how many possible succession paths, you would have as a monarch, which might be something that you're concerned about if this is the feudal era and monarchs kill each other all the time. Thankfully, we're not quite at that point. I personally have a belief that Queen Elizabeth is immortal anyway and will never die. So, you know, I don't think that's really a concern for the British royal family anymore, or at least it seems like it shouldn't be. But yeah, you could use it for that. Anyway, getting super off track here, so let's go ahead and go back to our actual goal, which is, so now that we've computed the best successor, I need to store it. I need to store what the actual best successor is. And now, I've noticed here that, we've said that the best successor, if there is one, we're going to assign to a string. And so I'm going to use null as my sentinel value to indicate that we didn't have a best successor. So we've computed the best successor. Was there one? Right? Because there's a chance that none of these substrings were actual words. And so they don't have succession paths. They don't have word funnels that come after them. And so I need to make sure that best successor is not equal to null before I actually state that there was a successor. And now what I'm going to do is, here is the update stage of my dynamic programming. In dynamic programming, we usually have two stages. We've got a base case that is essentially where we store where we retrieve our result. And then we have a case where we store our result for later. So this is our storage stage. So what we're going to do is I'm going to put this in the map. So I'm going to say successors dot put, and I want to put our current word, so the prev word, and then the best successor to indicate that we had a valid succession and we were able to compute it. And now what am I going to return? The maximum funnel length. Right? I'm going to return the maximum funnel length just to indicate back to our previous method the length of the funnel that started at that word. Okay. So now that we've done this, this should work. This should work to compute the best successor for every word, starting at a given word. I'm gonna hedge my bets and say that I think this works, but I know that this is confusing. I know that what I just did is complicated, and so if you have any questions, feel free to ask them in the chat. If anyone here is not one of my students, this is an educational stream, and so if you have any questions about what we're doing, totally feel free to ask them, and I'll be happy to answer any questions that you have about what's going on, or even just any questions that you have about the editing environment, or about where I got these problems, or why I do this, or about me, or what on earth is behind me, or anything like that. Feel free to ask. Now, I'm going to leave this up for a second, just so people can kind of chew on it. And while I leave that up, and hopefully I'll leave it up so that you can see it, well, maybe not really. I'm gonna go away for just a second, because I want to actually determine that the successor worked. So I'm going to print my successor map. I'm going to return null as my array list. And so I'm going to run the JUnit test. They're all going to fail. But I'm going to leave this code up here and run this so that I can see whether or not all this stuff actually worked. And then in the chat, Sarduck asks, what's your opinion on IKEA? I like IKEA. I think IKEA is pretty cool. Actually, a lot of the stuff in my house is IKEA. The house behind me is sorry, not the house behind me. This isn't a house, this is an apartment. But the couch behind me is from IKEA. My desk isn't from IKEA, it's from Costco. But I have a wall clock sitting here beside me that is also from IKEA. I have table and chairs from there. Yeah, lots of my stuff is IKEA. Also, the meatballs are really good. You know, whether or not they are horse is actually not that much of a concern to me. They taste good. If they're selling them in the US, they pass food inspections. And so, you know what? If those meatballs are horse, then I have learned that horse tastes kind of good. Question, isn't IKEA like cardboard? Yeah, Prince Logic, IKEA meatballs are incredible. They are. They're super good. And Prince Logic, isn't IKEA like cardboard? And General X-Red asks, yeah, it's particle board. Yeah, most stuff you get from IKEA is a material called particle board. Some people will actually split the definition of particle board into saying by, what is it? I think it's the fiber length. So you have like MDF versus LDF for medium density, low density. And what that essentially says is the length of strands of wood that you have in the board. And people like to kind of crap on particle board because like it's lightweight and it's cheap. But actually, just from an engineering standpoint, so I used to be on a robotics team. And so I did all kinds of, you know, kind of fun robotics type stuff. Particle board is stronger than just a sheet of wood. And plywood especially is actually way stronger. And so, yeah, and so if you want something that's actually super durable, then you want something that's either particle or plywood, because it's going to be stronger and last you longer. And so, yeah, so that's my 2 cents on IKEA. Yeah, you're right, in that the materials are cheaper, but that doesn't actually mean that they're any worse. And I think that a lot of stuff they have is good. Plus, IKEA's like adult Lego. I like things that are adult Lego. I built my own PC. That's just fancy Lego for nerds. IKEA is just adult Lego where you build furniture. So you know what? But IKEA is good. IKEA gets an applause. I quite like their stuff. And yeah, General X Red Robotics, let's go. Yeah, robotics is super fun. I like doing it. I did the best competition, which is a Texas regional competition. It is nationwide, but we never did the nationals because we didn't think it was a very good use of time and money. But yeah, so we did the regional competition. It was always super fun. I really enjoyed it. I was the programmer for our team, and we always did some super, ours was honestly really try hard in that, I ended up using, a completely different tool chain from the one they gave us. I used our own real-time operating system that I ended up making some modifications to, that ran our own library for controls and stuff like that. Mainly just because I wanted it to run a lot faster, and I thought that that gave us a competitive advantage over the other teams, in addition to the fact that I learned some really complicated control algorithms for steering, and so our steering was, like, really, really good and comfortable. Everyone always commented on how good our steering was. Anyway, that's enough humble bragging from me. You did Vex, Prince Logic. Yeah, Vex is kind of interesting. Best uses the Vex cortexes, but we didn't use the, like, other Vex parts. And Expo Seed, you used to do FRC. Yeah, that's cool. We wanted to, but our robotics team didn't have enough money to do FRC. FRC is expensive. And so we couldn't do that. We did do FTC one year, the, like, kind of scaled down cheap version, the first tech challenge. But that competition was super disorganized. I didn't like it. Anyway, that's my kind of sense on robotics. And yeah, it is. Yeah, it is. And General X-Red, General X-Red, this is why you see common use between Lego, Build PC, and Battle Stations. You do. I used to be subscribed to 2 of those. I'll let you guess which. And to put a lot of work in fundraising. Yeah, we weren't allowed to fundraise. Our school actually didn't let us fundraise. I went to a fancy private school that forbid external fundraising because their kind of view on it was that any funds that we bring in should be allocated to the common pool and then allocated proportionally to different activities around campus. And so the only type of sponsorship that we ever got was a Chipotle down the street from us gave us free burritos. That's the extent of the sponsorship that we had. Yeah, XOC, no fundraising. Yeah, no fundraising, unfortunately. Which kind of sucks, but hey, you know, it's what it is. It's what it is. Yeah, sponsorship doesn't sound awesome. I mean, it's food. I mean, like, it's free food. Like, Chipotle's not super cheap. I like Chipotle. Going up a little bit, XOC asks, why do you have your line number show the offset? Yeah, that's because I'm using Vim keys. So yeah, I'm not actually using like arrow keys, I'm using the Vim keys. And the reason that I have the offsets is because in Vim, you can prefix an operation by a number to specify how many times to repeat that operation. And so for example, the key to go up one line is K. If I wanted to go up 11 lines, then I could type 11K and jump right to where I'm going. So yeah, that's why I do that. Yeah, that's why I do that. Sponsorship sounds awesome. Yes, it does. Yes, it does. Java or Python? Java, I like static types. I like static types a lot. And so yeah, Python kind of rankles me a little bit. I use it for interviews though. I always use Python for interviews. Because Python is honestly basically executable pseudocode. And so it cuts down on the amount of like syntax thinking that I have to do. And so yeah, Python's great for that. Until of course you get to the point at which Python is inconsistent and then it annoys you, but hey, it's what it is. Tried learning Vim, just gave up and used Nano. Yeah, Vim is a time investment, but if it's something that you're dedicated to, and I personally am dedicated to it because I think that you can do super duper cool stuff with it, then I think it's actually a pretty worthwhile use of time to just get used to it. I learned it around, I think at this point, we're going on 8 years ago. I learned Vim, and it served me well ever since. And at this point, it's so ingrained in muscle memory that, for example, if I wanted to change, let's say that I wanted to change that word lexicon, like, I don't even have to really think about what I'm doing, I can just type the keys and jump straight to it. So yeah, if you feel like learning Vim, it's super cool. If you go to the Vim subreddit, they have all kinds of resources for learning. Let's see here. Fisherman 433. I start uni soon. Get to choose between C++, Swift, Java, C#, and Python. Whoa, you get that many choices of programming language? That's super cool. I mean, so yeah, so I'm a TA for a data structures course at UT Austin, and we don't give them a choice. The course is in Java. You have to use Java, and so that's really super cool that you get to choose. I would say of all of those, the best one to, I guess, start with, as you've mentioned, I think would be Java. It's been around for a super long time. It will continue to be around basically into the foreseeable future. It is honestly a really powerful language. More recent versions of it have super cool stuff in them, and I'll show you maybe a little bit of that later. And so yeah, I think that Java is actually a great language to work with going forward. It runs on... Prince Logic quoted the old Oracle installation screen. It runs on 3 billion devices since the 90s. Yeah, and it's interesting that it's always run on that exact same number of devices. I guess no one's ever actually made a new Java installation. The numbers just always stayed the same. And yeah, and it's used for almost everything. You're right, it's used for backend. It's used for microservices. Yeah, totally. Yeah, so Java, I think, is a great language if you, just for general learning, if you're just starting to learn CS, then I think it's a wonderful language because you don't have to deal with stuff like you would in C++ about manual memory allocation, stuff like that. You'll learn that later in a computer architecture course. Just for a good foundation to learn about data structures and algorithms and basic programming, I would go with Java. Java is nice. And yeah, you can use it for all kinds of stuff. You want to do web programming, you use Spring. Done. You want to do low latency communication, you can totally do that. There are trading firms in New York that use Java for high frequency trading. The fun thing is that, I'll tell this story later actually, but I'll tell this story once we're done with this problem because it's really kind of funny about how they use Java, but we'll get there. And you want to transfer to UT Austin? Yeah, totally. Yeah, come to UT. We'd love to have you. yeah, we would love to have you in the CS department. It's honestly a really great department. There are downsides, but overall, I'd say it's the absolute best CS education you can get in the US for the amount that you would pay, which is pretty low. Where are you going now, Fisherman 433? Just out of curiosity, where are you? Yeah, where are you gonna be starting? Oh yeah, also love the piano. Yeah, thanks. Oh yeah, it's actually an organ. It's a pipe organ. So I've got 2 manuals, all the different stops, and then also a rank of pedals down below. On another stream, not today, but maybe next week, I can play the organ for you. My current piece, unfortunately, isn't quite up to muster to do that yet, though. But anyway, yeah, we'll keep chatting, but for now, I'd like to continue with our problem a little bit. And I realized that I have an issue. I got a null pointer exception. And that sucks. Oh, right. And that's because, the funnel that I was returning, was null. I just set that to return null by default. And that was kind of a dumb decision. Because, my tests are checking the size of the funnel against an expected size. So I'm going to change this now. I'm just going to return a new empty array list, just so at least that call will succeed and so I can see the actual result. Now, as I run this test, you'll notice that I have some output initializing the lexicon and then accessing it. That's because the vast majority of this runtime has to do with the lexicon. Constructing this data structure is not very slow, but it's also not fast. Constructing the compact directed acyclic word graph that we're using isn't the fastest thing in the world. It is itself extremely recursive. I mean, many of the methods that are used in the construction of this thing are recursive. In addition to the fact that it has to use a lot of memory to store intermediate nodes, it involves this data structure called a register, that is used to determine the states that we've already fully resolved. So yeah, it's pretty, it's complicated. So the majority of our time is spent doing that. And, oh no. Oh, we've got a bit of an issue. Oh. Oh no. Oh. Uh-oh. Well, that's not good. So, our map is always empty. Our map is always empty. What? What happened there? Why? Okay. All right. Let's debug a little bit. Let's debug a little bit. Do you think it's viable to use VS Code with learning Java? Should I use IntelliJ? I honestly would just spring for IntelliJ. If you're a university student or even a high school student, JetBrains will give you a free license for it. And I think that the autocomplete and the refactoring tools and the static analysis that it gives you are way better than what you get via the Eclipse language server and VS Code. So yeah, I would just spring for IntelliJ. In my opinion, it's the best way to work with Java by far. VS Code for life. I mean, that's, honestly, more than what tool you use, the best thing to know, the best thing to do is to learn your tool well. And so if your choice of tool is IntelliJ, learn IntelliJ super well. If your choice of tool is Vim in a console window, then learn Vim in the console really well. If you're using VS Code, then learn VS Code and the Java extensions that you use and the things you use to run code in VS Code really well. You just want an environment in which you're comfortable and proficient so that you don't have to spend time messing around with the environment and you can focus on your code. I feel like you're the type of person with 12,000 answers, or 1,200 answers on Stack Overflow. I actually have never answered a Stack Overflow question. Now, maybe this makes me selfish, but I have never answered a Stack Overflow question, partially because Stack Overflow's gotten to the point that I think it has every possible question you could ask anyway, in addition to the fact that I just like to spend more time writing code and teaching code, kind of like we are now, versus answering people's debugging questions on Stack Overflow. I just don't, it's not super fun for me. Hello, Woolly Mammoth. Hello, hello. Hello, hello. How's it going? How's it going? What is up? Expo C, never answered a question because you don't have an account to answer with. I just use my Google account. I save questions, I star questions, I upvote stuff. I don't answer. NetBeans. Oh, wow. Okay, William Mammoth, one of your favorite topics. Awesome. I'm super glad that you like recursion. It's one of my favorite topics too. And this is recursion with DP. So I think this actually covers most of people's usual favorite CS topics in terms of basic data structures and algorithms stuff. Let's see here. Oh yeah, so anyway, on NetBeans, while I debug this, I started off using NetBeans. When I was first learning Java, when I was in 6th grade, I used NetBeans for a while. And honestly, it's a pretty good IDE. I don't have anything against it. I just think IntelliJ provides a little bit more assistance by default, or is just a more comfortable environment for me. Am I a competitive programmer? No, I'm actually not. I tried competitive programming for a while. It just wasn't my thing. I like working on long-term, large-scale projects a lot more. And yeah, so I just prefer that kind of problem-solving methodology versus doing like short problems that aren't necessarily as generally applicable. Oh yeah, General X read an Expo Seed. Yeah. Started with NetBeans when you first started learning Java in middle school. Yeah, me too. And honestly, I think that the reason I used it is because Oracle encouraged you to use it. Like, it's what the Java tutorials were in, and so I think that's why I used it. And probably why y'all did too. And yeah, I'm covering small short problems for now, and yeah, I am. That's because this is kind of a review for my students, and it's kind of just a chance to work with some fun stuff that I might not actually be able to ram into a project. I'll do some streams where I work on projects later. I've got a really cool project queued up working with the Mayan calendar that I'll stream maybe in a few weeks, but for now, we're doing Recursion because my students have an exam on it next week. And honestly, Woolly Mammoth, are you a competitive programmer? And if so, could you sell me on it? Could you make me think that it's fun? My students, my CS students, the students in the class that I TA for at UT. Yeah. And so that's kind of the big purpose of this stream, but it's also just to have fun with weird data structures and recursion and stuff. Anyway, yeah, we got an issue, and that was that my best successor was always null. That's a little bit annoying. Little bit annoying. And now, I have a weird theory, and I don't know if this is gonna work, but I'm gonna do it. I'm gonna set the maximum length by default to -1. And this may just be me being crazy, but I think this is an off by 1 error, and so I'm gonna do that. Well, I maybe read a few things more from chat. Nope, still empty. That didn't do it. Anyway, you're not one self-taught, but follow a ton of the top competitive programmers. Okay, cool. And had to learn it for interview prep. Oh yeah. Like if you're interviewing, this type of stuff is, it's super common, and especially your kind of like big tech company interviews. So if you want to work for like Google, or Amazon or Bloomberg, where I worked, or one of those places, then yeah, you need to know this type of stuff. Pretty much in and out. Okay, so that didn't work. So let's see here. So my problem now is that, let's see here, that I'm never getting proper successors. So what I'm gonna do now is actually use the debugger here to step through and see what's happening. What's happening with this? Fisherman 433, do you have a lot of questions answered on LeetCode? I actually don't. I don't LeetCode very much. I did a few of the most common problems just so that I would be familiar with them. Once they... Wait, what? Oh my gosh, I'm so dumb. I forgot to actually call the recursive method. I said that this would happen earlier. I told you all that I would do this because I do this all the time. I forgot to actually do the recursion. And so, okay, so I need to call find successor. I'm gonna pass the start word, my lexicon, and my hash map, and let's see if this works now. Oh my gosh, I knew it. I knew this would happen. I knew it. I told you. I called it. Anyway, yeah, do I have a lot of questions answered on LeetCode? I don't. I do it occasionally. Some of the problems are kind of fun. I really like the, like, compiler or interpreted relator ones, because that's, like, my interest in CS. But I don't particularly do a lot of, LeetCode. I mean, if it works for you, that's great, but I honestly find that just doing, well, obviously being a TA, and then doing stuff like this, where I do these kind of problems that I come up with that I think are fun, serves just as much of the same purpose. So, I mean, this is kind of like LeetCode. This is just, I mean, this would be like, what, a LeetCode hard? Like, this, using recursion and DP, I guess this would be like a double black diamond LeetCode question in some way. Woolly Mammoth, can you ask what school I teach at? I teach at UT Austin. University of Texas at Austin, yeah, as people have said in the chat. I'm a teaching assistant for an intro data structures course. I'm not a professor. I have no interest in being a professor. I'm not an academic. Yes, I teach at UT Austin. Yeah, one of the top CS schools. Yeah, it's, as I said just a little bit ago, I think it's honestly the best CS education you can get for the pretty low amount that we charge. In addition to, actually, I personally think that we have the best CS program in the country. And it's because the professors we have are great. The students we have, many of whom are in the chat, are fantastic, and super driven and super willing to work hard and learn. And so, yeah, I think that, yeah, I personally think we have the best program in the country. How much does it cost? If you're an in-state student, so if you're from Texas, it's what, $5,500 a semester or something like that? It's honestly really cheap. And room and board in Texas, in Austin, is a little expensive, but it's still a lot cheaper than a lot of other schools. So, like, my expenditure per semester tops out at around, like, $12,000 in total for tuition and room and board. It's honestly a really good deal. Yeah, thank God for in-state tuition, as Expo Seed says. Yeah, thank God for in-state tuition indeed. Yeah, it is super nice. Yeah, I think it's a really nice resource that we have. Out of state in California is insane. Oh yeah, when I was doing college apps, I applied to the UCs, and wow, they cost so much if you're an out-of-state student. Yeah, so that calculus was not worth it for me. And so yeah, I ended up sticking with good old UT here in Texas, and you know, it has been a great experience for me. Yeah, moved from California to Texas and kind of wish you stayed. Oh, I'm sorry. Is there something about... Yeah, I guess what are you not liking about it? It's always good to get kind of other opinions. Like, what's... Yeah, I guess kind of what's your qualms with Texas? I know that, like, the politics aren't great, and I don't agree with majority Texas politics either, but yeah, I mean, I guess just, yeah, what's kind of, what's your sticking point? Anyway, yeah, so while we talk about this, let's actually look at our problem. It worked! It worked! We found successors. Once you actually call the recursive call, the code works. And that, I know, is just this mind-blowing concept, but, you know, it's nice. And so, now that we've done that, the only thing that remains is to find the actual successor for the given word. Oh yeah, so yeah, out-of-state fees. Yeah, out-of-state at UT is expensive. That is true. We kind of fleece out-of-state students, and I'm sorry that we charge you so much. I think that we should lower out-of-state tuition. Politics are Yeah. I mean, if you're more liberal in Texas, then it's not great. And, you know, I don't know, I guess this isn't an official university thing, so I can give you a little bit about my political views. Like, I'm a liberal person. I am also frustrated by Texas politics, but, you know, if it's your thing, then, you know, that's great. And yeah, out-of-state fees. Yeah, that's stupid. And the humidity. Oh yeah, the humidity is bad. At least we're not in Houston. If we were in Houston, then it would just be death. I mean, no, Houston is way too humid for me. It's like you're drowning by breathing. Yeah. And yeah, what would you see community college and try and transfer? So you'd be a resident. That's the way to do it. Yeah, Fisherman 433. That's the way to do it. I have a friend who did the same thing coming to UT, although he actually worked for a year full-time while being a student, which is just absolutely crazy to me, and then got in-state tuition. So yeah, there's a way to get in-state tuition, then yeah, do it. It's a good path. And yeah, and General Xrad mentions voter turnout. So here's the point in the stream at which I'm going to look directly at the camera for a few minutes. I'm going to be like Joe Biden in a presidential debate and say, we have an election coming up. If you haven't voted yet, and you are eligible to, then you should. It is everyone's civic duty as American citizens to vote in our elections. Personally, I think that Australia has a wonderful idea of making it illegal to not vote. And my Australian girlfriend behind me is making dissatisfied noises at that, but whatever. And so, yeah, so if you can vote, you absolutely should. This is the future of our country. If you either like or don't like what is happening in US politics right now, and you should probably have an opinion on either of those things if you've been really paying good attention, then go vote. Go vote. The election is on November 3rd, next Tuesday. Make sure that you can get to a polling place. If you need help getting to a polling place, or you need help finding what your polling place is, then send a message in the chat. But yeah, please go vote. It's the future of our country that is at stake, and so all of this matters a lot. So yeah, please go vote. Please go vote. Your vote counts. I know that sometimes it doesn't seem like it does, but your vote is actually important and can make a difference in the future of our country. So go exercise your franchise, do your civic duty, go vote in the election, and that's all I have to say about that. I think voting should be a choice. General X Red. Yeah. I mean, yeah. Yeah, that's true. I mean, yeah, there are arguments as to whether or not mandatory voting is a good thing. I mean, I'm of the opinion that it would lead to having a more informed citizenry in general, because people would have to think about it, because they're going to have to go vote regardless, but there are totally arguments for and against that. Doesn't Australia have ranked choice voting? Yes. Yeah. They do have a super cool ranked choice voting system. We use first past the post voting. It's bad. I'm not going to get into it. In a future stream, we may write the Australian voting system, actually. It's kind of a fun challenge. As Prince Logic said, you did. And blue votes in red states get wasted because of gerrymandering. That is true. If you've ever looked at our voting districts, then yeah, that becomes apparent. But anyway, we're doing recursion. We got a little off track. We've got to actually do recursion. So now that I've generated my successors, I want to find the successor of our starting word. Let's do that. I'm going to have my array list of string. I'm going to call it the funnel. Oh, can I show the code? Oh, right. Sorry. Oops. Sorry about that. Let me switch back to the screen view there. There we go. Okay. Unless, of course, you want to see my beautiful face anymore, but honestly, you probably don't. So yeah, let's look at the actual code. So we're going to generate a funnel. Say new array list. And let me give that a slightly better name. And now what I'm going to do is I'm going to write a loop here that's just going to find the successor of each word subsequently until we reach a word that doesn't have a successor. And Woolly Mammoth, can you link to the problem statement or prompt? Yeah, so this problem, a simplified version of it was on the Daily Programmer subreddit. Here, I'll post a link in the chat to the problem statement that I got this from. Oh, right. IntelliJ hijacks your copy paste if you use Vim keys. Let me copy that as plain text. Paste that in the chat. Yeah, there we go. But we're doing a variation on this problem. The problem statement there only says that that you need to find the length of the funnel. We're doing the much harder version where you find the funnel itself. But yeah, there's the general statement, if you want to read that. So yeah, so now what I've got to do is I've got to loop through my successors, finding the successor for each word until we run out of successors. And so I'm going to say, so string successor. I already have something called successors. I don't like making plural distinctions in code, so I'm going to just call this like next word. And we're going to start off with my starting word, of course. I just want to keep that. Woolly Mammoth, kind of like path reconstruction. Kinda. Yeah, it is actually, by tabulation. It is kind of like that. Yeah. Yeah, that's not a bad analogy. I'm not super familiar with the path reconstruction problem. It's not something that I've looked at too much, but the general structure, at least to me, seems like it would be somewhat similar from what I know about it. So now what I want to do is I want to keep looping through this, provided that I actually have a word. And so I'm going to say, so okay, so while we have a next word after this, and let me make sure that I'm doing this correctly. I want to add this word to the funnel. Word funnel.add next word. And now what I'm going to do is I'm going to get the next word, so I'm going to say next word. Oh, and I need to say next word is not equal to null, right? This isn't C. We can't just assume that null is a falsy value. Next word is going to be successors.get next word. And now at the end, we're just return our word funnel. And now that we've done all of this work, let's see if it works. We're going to run this. And just let it run. And we've got some unit tests here. we've got some unit tests here that should be able to validate that we have valid funnels. And there we go. All right, all of our tests are now passing. Nash took 25 milliseconds, which was a little bit slow, to be quite honest. And honestly, that might be due to, like, JVM startup time getting aliased into this runtime, or getting included in this runtime. But then the other ones you can see are super fast. 2 seconds, 2 milliseconds, 1 millisecond, 0 milliseconds for some of these. And yeah, and so the reason we're able to get these super fast runtimes is, well, just because of all of the optimizations we made. We did dynamic programming, where we stored the best successor of each word, so we didn't have to recompute the paths. We used this super complicated, super cool data structure called a compact directed acyclic word graph to store our lexicon so that we could very quickly determine which words are in the lexicon without eating up all of the memory on my system. And so that is kind of how, that's how we went about doing this. And I'm going to go ahead and put the recursive methods back on screen so that you can see those, in case you have any questions about them. But yeah, that's, in my opinion, this is what I would consider a really good implementation of this problem. If this were a technical interview, I'd definitely move the person on to the next round. If this were my course and someone wrote this as an exam solution, then I would be exceedingly pleased with that they were able to come up with this. So yeah, so there you go. That's the word funnel problem. Kind of more complicated than the last one. Definitely got some interesting concepts here. We have tail recursion in this method. We have dynamic programming in this one. We have recursion in recursion. But you can see overall, the algorithm is still relatively straightforward and passes this same recursive backtracking formula that we've been talking about all along. Yeah, Woolly Mammoth, trading space for time. Oh yeah, and shortest path problem solved by DP. Yes, yeah, exactly, right. That is exactly what we're doing here. Yeah. Correct. Yeah, this is a shortest path problem, roughly, that we have used dynamic programming for. Yeah, and trading space for time. That is what DP is, yeah. We get better runtime, use potentially way more space. And this data structure is also a time-space trade-off. We're trading off the fact that making one takes a pretty long time for the fact that the space requirement that it has is really low. Looks beautiful. Thank you, Fisherman. Thank you. Glad you like it. So anyway, so that is our word funnel problem. It's honestly, in my opinion, one of the cooler problems that we can do that are relatively easy to illustrate. And this solution that we've kind of stumbled into gives you a really great overview of almost all of the things that we may run into with recursion in real world recursion, where we've used tail recursion to optimize this method. If the Java compiler, if we were on the Project Loom compiler, then we get tail call optimization, and this would be a for loop written recursively. We're using dynamic programming to avoid unnecessary recursive calls, and here we have bog standard tail recursion. Tail recursion with an optimization criterion of finding the longest possible funnel length after this word. There we go. There's this problem. All right, and so now, for the remainder of the stream, as I said a little bit earlier, this is kind of an exam review for my students, and something that they're going to have to work with on their exam is stacks. We cover stacks in our data structures course at almost the same time we do recursion because we talk about the call stack. We talk about the call stack and how recursion affects the call stack, and how, as we do different recursive calls, then we may actually be able to reuse space on the stack for subsequent recursive calls. We talk about the stack a lot, and so I would like to work with stacks for a little bit. And the way that we're going to be working with stacks is to do something that I personally think is super fun, and we're going to write an RPN calculator. So RPN stands for reverse Polish notation. For anyone who doesn't know, RPN is a representation of it's a representation of an arithmetic expression. So let's say I have an expression like 4 plus 7 times 3. RPN is a postfix version of this expression. So this expression in RPN, we have to consider order of operations so that we get the correct result. And so this expression would convert to 7, push 3, multiply, push 4, add. Because if we think about how we're doing this arithmetically, what we do is we get a 7, we get a 3, and we multiply them, and then we add 4 to that. This is doing the exact same thing, but where we put the values on a stack, and our operators operate upon that stack. RPN is a really great way to express arithmetic expressions. HP calculators of yore, and even some of the modern HP calculators, use RPN as their input method because people who are well-schooled in it make the claim that it's substantially faster than your standard infix notation. And me, as someone who doesn't know how to use a 10-function calculator, or sorry, a 10-key calculator, or like a 4-function calculator very well, yeah, I actually prefer RPN. Like, the calculator that I use on a pretty regular basis is an emulated HP 48G, which is a super powerful RPN calculator that has a computer algebra system. And so, yeah, I can attest to it being a very effective way to do problems. And Exproceed says there are languages like Lisp that use RPN. Lisp is actually the opposite. Lisp is what we call traditional Polish notation. Lisp is prefix. And so if we get that same expression back from earlier, in Lisp, the way that we would write that is we go outside in instead of inside out. And so what we would do is we would say, so we're going to add 4 and the product of 7 and 3. And so we multiply 7 and 3, get a product, and then add that to 4. Yeah, you misremembered. That's totally okay. That's how it goes. Yeah, William Mammoth, you have no idea what these are, as in terms of RPN, or just kind of generally what we're doing. If you're confused, then, like, you know, let me know what's going on with that, and I would be happy to let you know. Oh, are there languages in RPN? There are, yeah. So there's a programming language called Forth that was well known for having basically RPN as its input method. And so in Forth, if you wanted to store the value, let's say you wanted to store 7 times 3 in a variable called x, you'd say something like 7 3 times symbol x store. I don't really know Forth, but it would look something like this. And the calculators are programmable in a language called RPL, which stands for Reverse Polish Lisp. That's the language that the HP calculators were programmed in. I honestly don't know it too well. I always have to look up a reference card if I'm trying to write a macro for these calculators. But yeah, there are programming languages that use RPN, that use postfix notation, and they're actually kind of cool. I kind of like working in them. Familiar with Common Lisp and Clojure, just a tad. Yeah, I'm using Clojure for a class right now. I like it. It's okay. You know, it's unfortunate because you try and do Lisp things in it that don't work. Like, you expect tail call optimization like you would in Common Lisp, and then you get a Stack Overflow. And so, yeah, it's kind of like, it's Lisp, but in my opinion, it's Lisp that I constantly get frustrated with because I think things will work that don't. And I have used just pure Lisp, but it's Emacs Lisp to write, you know, Emacs plugins and stuff. Yeah, so anyway, so we're going to be implementing RPN today. And the thing that we've got to work with here, I have done Haskell. Yes, I have done Haskell. I would not do it much more by choice. But I have done Haskell. It has some interesting ideas. If you're okay with your code being inscrutable to the average reader, and honestly probably to you the next day, and running really, really slow. Yeah, I'm not too big of a fan of Haskell, but the syntax is actually quite nice. So yeah, Haskell is okay. I've used it for some stuff. I wouldn't reach for it again, probably. There are better options. I'd reach for OCaml instead, if I needed a compiled functional language. But anyway, so we need a stack. And Java provides us with a stack interface. And, well, it doesn't provide us with the stack interface, it provides us with the stack class. And the Java stack class is less than fantastic. The Java stack class is actually basically a relic of the Java of yesteryear, the pre-generic collections library. And so the stack interface the stack class is super duper limited. It's not very efficient, and overall, I just don't like working with it too much. So I've actually written for us a data structure that can be used as a stack. This data structure is what I call a ring list, but you've probably heard it referred as a ring buffer. So a ring buffer is essentially... You tried using the stat class on the anagram assignment and it ran slower than a normal array list? Yep. Yeah. The Java stat class is synchronized, so it has to do a semaphore acquisition. No, not semaphore. It's Java. Monitor acquisition and a bunch of other stuff. It's slow because it has more overhead. If you were writing this multi-threaded, then you'd totally want to use probably the stat class. But for our purposes, this is single-threaded. We don't need it. But yeah, we're going to use a ring list or a ring buffer. And the ring buffer, the way that this works is it's a data structure you may not have heard of before. They're not the most common. They're not the most common data structure in the world. But it's basically like a standard array-based list where we have a number of elements in a list. But the list is not guaranteed to start at the beginning of the array. So if you come down here, you'll notice that our our ring list stores not only the size of the list, but also the index at which the actual values start. And the super cool thing about ring buffers is that once you get to the end of the list, it wraps around to the beginning and continues with indexes from there. And the way that we traditionally express this is using a modulo, as you can see in this method here called index. That's used throughout this class to compute the index of an external facing index. So an index that you might give to the user, a zero-based index, to an index into the ring buffer. And these things have lots of super cool performance properties. One of them is that removing from both the front and back is constant time, in addition to accesses being constant time. And so in essence, you get all of the benefits of a doubly linked list without the drawback of having order n indexing operations. They're also super cool because you can shift the start point of the array. If you remove something from the list that's in the first half of the list, normally if we remove something from an array-based list, we'd shift everything that's after it down one position. But in a ring buffer, we can either shift down or we can shift up from the front. And what this means is that remove operations have to shift at most half of the list instead of the whole thing. And so yeah, so basically, ring lists are better than array lists in almost every way. They're usable as both stacks and queues and decks. They're usable as basically all of our list-based data structures. You see here it implements the deck interface, and that's what we're going to use for our stack, because that's what the Java standard library recommends you use to implement stacks nowadays. Stacks and queues. They use the deck interface. Is there a reason not to use ring lists? You know, to be quite honest, there are a few. One of them is that they're harder to synchronize, and so if this is multi-threaded, then they get a little bit trickier to synchronize, because the part of the list that you lock isn't necessarily able to be determined quite as easily, but honestly, I could probably write a synchronized version. It wouldn't be too bad. The other downside is, I guess, that you have to store an additional index, and accesses are a little bit slower because you have to perform a modulus. So you have to compute indices. But for our purposes, it's more than fast enough, and this overhead, in my opinion, combined with all the other optimizations that we get, inserts, by the way, also you have to move only at most half of the list, because you can shift half of it, depending on where you're putting stuff, outweigh the drawbacks. And so these are, in my opinion, a better version of an array list. And I actually stumbled upon this implementation of an array-based list reading about the Objective-C standard library. So if you're a Swift programmer or an Objective-C programmer, then you're probably familiar with NS mutable array. That's essentially the Objective-C equivalent of the Java array list. NS mutable array is implemented like this. It uses a ring buffer internally. And so this isn't just me being weird. This actually has precedent in a major programming language's standard library. Like, if you have an iPhone, like I do, or you have a MacBook, there is almost definitely code running on that is using this exact data structure very frequently. So, yeah, super cool. A little bit of a peek behind the hood of how we do stuff. And honestly, a really cool data structure, in my opinion. Again, one of my other favorites. The corn dogs are still my favorite. But these are honestly a close second. Maybe not a second, but they follow very shortly there behind. And by the way, just in case you're wondering about, like, you want the source for these data structures or the problems that we're doing, I'm going to post a GitHub link in the chat a few minutes after I turn off the stream. I'll keep it going so you can listen to some wonderful Bach. And I'll post a GitHub link so you can actually access the code afterward. It'll be open source, GPL3, all that good stuff. Anyway, let's write RPN calculator. This is fun. So this is a little bit of a design problem because I'm actually going to be writing this from scratch versus having a harness like we did the past few. So I'm just going to call this RPN calculator. All right. So de novo, here's how I would design this class. I know that right out of the gate, I'm going to need a stack. Right? I'm going to have a stack here. There's no way to get around that. And so I'm going to go ahead and have a private ring list. And now this is going to be an integer calculator. So we're only going to be able to do operations on integers here. I could make it generic over any numeric type, but that's a little bit more than we really need to go through right now. But I'm going to have an integer stack. And this is going to be our stack. So this is essentially our value stack, where we're going to be using the standard stack methods on this. But just to clarify, in our ring list, the front of the list is the top of the stack. And you might be going, whoa, wait a second. That seems aggressively stupid to do that. Because here's the thing, right? If you put something at the front of the list, it doesn't have to shift everything after that. And my answer to you is that's why ring lists are cool. Constant time addition and removal from the front and back. And yeah, woolly mammoth, they are known as circular buffers. Yeah, circular buffer. Ring buffer is the term that you might hear more if you're in the embedded system space. But yeah, they go by different names. Circular buffer is another one. And yeah, maybe that would be a better honest name to call this. But because the Java standard library has this kind of has this custom of naming things by the way that they're implemented and then the data structure that they are, I stuck with that. So ring buffer implemented as a list, ring list. And honestly, that's all we need. This is all we need. So yeah, we're gonna have a stack. And actually, I think that a better way to do this would be to make this class not actually a class per se that we have to instantiate, but maybe a static class. So a class that we can just call out to pass it some RPN expression as a string, say evaluate this and give me a result, without having to actually make a new one. So what I'm going to do is I'm going to make this an uninstantiable static class. And now IntelliJ is telling me that uninstantiable isn't a word, and I tell it that it's wrong. But what I'm going to do is I'm going to make the default constructor private. And so what this will do is it'll say, now this class has no constructor. If I now go and I try and make an instance of RPN calculator, then it's going to tell me that I can't. It has no constructor. Hi, Kappa Votes. Welcome. We are currently playing with recursion and stacks. A little bit ago, we did some fun problems dealing with Morse code and some word games that we implemented using recursion. But now what we're doing is we are writing a calculator for reverse Polish notation expressions. So RPN being essentially a postfix way of writing expressions. We've already talked about this a good amount, but in case you want an overview of RPN and how it works, I'll go ahead and link the Wikipedia article in chat. So there you go. So yeah, so if you're wondering about RPN and kind of what we're doing, that is what we're doing here. So I'm going to make this a static class. And so what that means is that the only method I'm going to have in here is a public static int, right? Because we're computing integers, or we're using this for integers. I'm just going to have a method called calculate. It's going to take in a string with the expression. And that is it. So that is all we have here. All we've got is a method called calculate. It takes a string, and everything else we're going to do in this method or helper methods from this. And so now I know that by default, for any RPN expression, I need a stack. And so I'm just going to make one now. So I'm going to say ring list of integer. And this will just be a new ring list. And so here we've got an empty list. It contains 0 elements. And now what I need to do is the first thing that I have to do here is parse this expression. Now, parsing is its own can of worms. If this were a standard programming language and we were dealing with infix notation, then I would end up using an algorithm called Dijkstra's shunting yard to convert infix into postfix. It's in itself its own super cool algorithm. It's something that I personally have actually written before on the job to do expression evaluation. There's a link to that too. It was come up with by Edgar Dijkstra, a UT professorial alum, and so, you know, we have a little bit of territorialness with that too. But I'm gonna define this expression to be an expression like the ones we wrote, where we either have numbers or operations separated by spaces. And so the whole process of what would be called tokenization, where we separate this expression into different operations to perform, I'm going to be really lazy and just call expression.split on spaces. And actually, you know what? I'm going to be a little bit fancier with this. I'm going to split on all white space. And so it's going to be S+. And for those of us who might not be as familiar with regex, and that's completely okay, regex is weird and confusing, what this is doing is it's saying that we're going to split anytime we encounter at least one, that's what the plus means, white space character, which is what the \s means. So that's a brief overview of regex. And so now, given this expression, we're now going to have a list of tokens. And just to make sure that this works, I'm going to stop now to go ahead and print my array. And now Java's array class is, or Java's arrays are weird. They have like no methods on them. And so I'm just going to go ahead and print my tokens here. I'm going to return 0. And I'm actually going to make this an executable class just because I want to be able to iterate on this super quickly. So what I'm going to do is I'm going to call calculate, and I'm going to pass it an expression. The one we were working with before was 7.3 times 4+. And so if this is working, then we should have an array with 5 elements, a 7, a 3, a multiplication sign, a 4, and a plus sign. And let's make sure that that's what we get. And that is what we get. And Exposeed asks, why do you do double \s? Wouldn't that escape the backslash? It does escape the backslash. The reason that we have to do this is that regular expressions have these types of special escaped characters that mean certain character classes. So like, for example, \s means white space. \w means, I think, word separator. Something like that. Anyway, there are all these different kind of escape characters that we can use. But the problem is we're going to get interference if we only do a single backslash with Java itself, because remember that Java permits a backslash and then a character to escape that character, just like we would do new lines with \n. So to use the special characters in regex, we have to put a double backslash to indicate, hey, I want to retain the backslash in the string and then have the S and then the plus. So like if we print this, then we would get system.out.println, oh my, what on earth? .println, that exploded into like 8,000 different characters. Then you're going to see we get the single \s+. That's our actual regex. And yeah, Exposeed is kind of icky. It is. I'll admit that I don't like the fact that Java hasn't given us a raw string type. So for example, in Python, if you want to not escape regex, you can use what's called a raw string, which doesn't recognize escapes. And so, for example, if it's for Python, I could write this as r \s+, like that. And that would be the way that I could do that in Python without having to duplicate it. In JavaScript, I can just straight up do this. They accept slashes as regex delimiters, which is cool. It's an odd kind of parsing case, and it makes parsing JavaScript super hard, but, you know, it works. And so there are different ways to express that, but Java only gives us this double backslash to retain the backslash in the string. So you know what? We stick with what we've got. Hey, it's all we can do. It's all we can do. And now that we're moving on to this, I'm going to write, change our title here to writing an RPN calculator. Just to highlight what we're doing. All right. So now that I've got a tokenized expression, I need to be able to do stuff with it. And so we know that anytime we get an integer in our list, then what we're going to do is we are going to push it onto the stack. And if we get an operation, then we are going to execute that operation on the stack. And now, I've realized now that there's actually a slightly better way that I can do this than using regex, and that is instead to use Java's scanner class. I don't call it tokenizer. Actually, it's a tokenizer and it's a lexer, so I'm gonna call it lexer. And I'm gonna make a new scanner through this string. Can you get more than 2 digits in a row? You can get any number of digits that will fit in the Java integer type. So yeah, you can have a lot of digits in a row. And so yeah, you can push, oh, I see what you're saying. Like, could you have sequences of digits like this? And yeah, you totally can. You can absolutely have that as well. That's valid. We can push as much as we need, because remember, we've got this stack that's just gonna store all the values we have anyway. Okay, so now what I'm gonna do is I'm gonna use this scanner to loop through my string. And so I'm gonna say, so while my lexer has a next token, there are 2 cases. Case number 1 is that I have an integer. So we push it onto the stack. So I'm gonna say if lexer.hasNextInt, then I'm gonna say stack.push lexer.nextInt. Otherwise, our other cases, we have an operation. And we're going to get there. We're going to get to dealing with stack operations. But for now, I just want to make sure that this part's working here. And so I'm going to say string operation equals lexer.next. And let's just print it. And at the end of this, we'll also print our stack just to make sure that that's working. .println stack. And stack, by the way, of course, has a toString method. So here you'll see that we're going to get times plus 437. That's what we were expecting. Kappa votes us, have you written a compiler before? Like a whole one? I have. It's actually one of my ongoing projects. Is for a new programming language that I'm working on called Hudson that runs on the JVM, but has syntax that's essentially a mishmash of Haskell and Ruby. With little tiny bits of OCaml mixed in. And so it's a little bit of a hybrid. The whole goal is that eventually, once Project Loom comes out, it's going to have multi-threading that's very similar to Go's Go routines. And so it'll be super easy to do multi-threading in. And so yeah, that's kind of what I'm working with. I basically want to make, because OCaml's multi-threading situation is bad, I want to make multi-threaded OCaml that has syntax that I like a little bit better. Disabled account asks, why Hudson? It's called Hudson because I started coming up with the idea for the language when I was in New York. So 2 summers ago, well, and last summer as well, but I wasn't in New York. I worked as an intern for Bloomberg, who I'm now shilling for, and I hope are happy with that. Anyway, I worked for Bloomberg, and so I was in New York over the summer, and I was working on some kind of side projects alongside from work, just because, you know, I wanted to, you know, keep doing some other stuff that I found interesting in addition to my work, which was in its own right extremely interesting, but, you know, can't do it on the weekends. And so I started on this programming language project and started coming up with ideas for it. And I was doing this while I was sitting in Battery Park, which, if you're familiar with New York, or if you're not familiar with New York, is the park that's at the very southern tip of Manhattan. Manhattan being the, like, big island that is what we call New York City. And so, yeah, if we go on Google Maps, I search up Battery Park, New York. Yeah, there we go. That's where I was sitting. And you see, I was looking out over this body of water. And this body of water, it turns out, is the Hudson River. And so I figured, well, you know what? No real better language than, or no real better term for this language that I'm writing than the place that I'm currently sitting at. And so, yeah, thus the language called Hudson was born. More specifically, I was sitting like right, I was in front of the memorial. I was like right here. But yeah. And so, yeah, so that's where the language was born. It's called Hudson just because that's where I was looking out, in addition to the fact that one of my kind of targets for it is that it will be really useful for the financial industry, which in the US is largely based in New York. And so, yeah, that's the name. And that's why it's called that. Isn't the Hudson River poop water? The Hudson River is poop water. Don't swim in the Hudson. You will get many diseases. But, you know, it was a nice thing to look out on and see some water and waves and the Statue of Liberty that I had never seen before, being from Texas. So, you know, it was a cool experience. So I decided to commemorate that in the name of the language. Kappa votes. Is Battery Park in Deus Ex? I've never played Deus Ex. I've heard really great things about it, but I've never quite gotten to actually playing it. Maybe I will. I didn't know it was based in New York. Is it based in New York, Kappa, or is it just a similar name? And I'll let you... Yeah, you think so. Okay, cool. Very nice. Very cool. Okay, maybe I will play it then. Games in Manhattan are super cool. It's a really fun environment. Like the Spider-Man PS4 game that came out, super interesting. I play a lot of Flight Simulator, and I often find myself flying around Manhattan in general aviation planes, just because it's also kind of fun. But yeah, New York is cool. If anyone ever has the opportunity to work in New York, I think you should. It's really awesome. Oh, and Lego Marvel Superheroes, I guess, did too. Yeah, that makes sense. Those movies are often based in big cities. Either New York or Chicago is usually where those are. And free roam in New York. Oh, that's super cool. Nice. Huh, maybe I'll have to pull that up at some point. But yeah, so now we've got to the point where we've got a stack that contains our values. We've got the values themselves. We've got our operations. Now we need to be able to execute these operations. And now I've got to come up with some way to actually handle this stuff. So what I want to do is I want to be able to define my operations without having a massive switch statement or nest of if statements. Right? Now, I could very easily do this problem in like 5 minutes if I just had a giant switch case that I plugged every operation that was supported into and dumped those operations back out. Just in the switch case. But that's kind of lame. That's a lot of repetitive code. And so what I'm going to do instead is I'm going to use a map that's going to map from the string representation of the operations, so the name of the operations, onto what they do. And what I'm going to do then is I'm going to say here that I'm going to need a class for an operation. And now this is just going to be a really, really simple class. It's only going to contain 2 things. I'm not even going to bother writing accessor methods or anything that for it. I'm going to say it's a private static class called stack operation. And it's going to contain two values. The number of operands required to execute the operation. So this is the number of operands we need to successfully perform the operation. And I'm also going to store the actual function that is going to run. And so that gets to be a little tricky, because now what I'm going to have to do is, well, actually, I guess, you know, I don't necessarily actually need this class, but what I am going to need is a functional interface for the type of data that we're working with here. And so we are now going to have to delve into something that is, well, a little bit weird in Java. And that is, we're going to start working with functional programming. So let's do it. Let's do it. Now, my interfaces that I'm going to define here. I'm going to define an interface. Side interface stack operation. And Expo Seed, could you do it with lambdas? I could use lambdas, yeah, but I need an actual type. I need a type for the lambda because I'm going to store them in a map. And so I need to define this interface just so that I can specify what, just so I can specify the operation that we're going to perform and store at the map. And now in Java, a functional interface, which you can annotate actually with this annotation functional interface, and it's going to tell me there's no target method. We'll get there. What it takes is it's going to have a single method. And so what I want to do is I want to have a method. It's going to return an int, and it's going to take in the stack. And so it's just going to take in my ring list, or really we should specify that this is really just a deck, since that's what the ring list ultimately is with the stack. And so each method we write is going to be some variant of stack operation, a method that takes in the stack and performs some operation on it. And so let's go ahead and start writing this. So now I'm going to support, just to start, I'm going to support 4 operations, very simply. Addition, subtraction, multiplication, integer division. Bog standard, super simple, but will serve as a really good basis for the stuff that we're going to do in a little bit. And so what I want to do now is I want to say, actually, do I want anything else? No, I don't. Okay. Is we're going to make a map. So a private static hash map from string onto stack operation. So note, so yep, here we are mapping, and yeah, I'll import that from the name of the operation onto what it does. And I'm going to call it operations. And so these are the operations that are supported by our RPN calculator. And now I need a way to actually instantiate this map. And I noted that we don't want to be able to make instances of this. So now I'm going to do something that may be unfamiliar to even more seasoned Java programmers. And that is I'm going to write a static initializer for this map. This is just something that runs at program startup to initialize our data structure. And so what I'm going to do is I'm going to say, okay, so I want my hash map to contain, we're going to start off with addition. And the way the addition is going to work is we're going to pass in a stack. And then what I want to do in the case of addition is I want to return stack.pop plus stack.pop. And so we pop 2 values and we return their sum. I'm now also going to do this with subtraction. So now I'm going to say put minus, oh, not 0, put minus stack.pop minus stack.pop. Multiplication, same thing. Oops. Oh, can't do that. There we go, minus times. And now the only other thing we've got to do now is division. And division actually is, oh boy, okay, so now we get the Halloween toccata. Happy Halloween, a day late, everyone. The gods of music have decided that we're going to be listening to that. I've realized that I made a bit of a mistake, and that is that I actually want to subtract the second value we pop from the first value, not the other way around. And so what I'm going to need to do then is I'm going to need to change this slightly. And so I'm going to need to store the, what do you call this? The subtrahend is going to be the first thing I pop from the stack. And I'm going to return the next thing on the stack minus the subtrahend. And division is going to end up working in a very similar way. And so our denominator is lower on the stack than the numerator. And so I've got to get the denominator, subtract that, and change the operation to division instead of subtraction. Subtrahend is the thing that we subtract from a number. And so if you have like x minus y, y would be the subtrahend. These are like super kind of weird, old, archaic math terms that I guess we don't really hear too much anymore, but they are kind of, they're still around. And of course, I need to actually make this a new hash map so that we don't get a null pointer exception. And Kappa votes, is writing the backend difficult even with LLVM? Yeah, so I used LLVM, and I will say that the backend is absolutely the hardest part of writing a compiler. I mean, actually, my current language is on the JVM, so I haven't worked with LLVM recently. But yeah, the backend is really difficult, especially if you have a powerful type system like my language does, then it can be extremely difficult. But, you know, it's just one of those things we've got to deal with, and the backend is also the fun part. Now, anyway, now that we've got our operation, now we want to actually execute this operation. And so what I'm going to do is I'm going to say, so stack dot push, and I want to push the result of executing this operation on the stack. I'm going to say stack dot push, and now I'm going to say, let's see here, I want to get this, get the operation to perform from my map. And so I'm going to say operations dot get operation. And now I'm going to call the operate method with my current stack. And so here what we've done is we've said, okay, so, and this is a little bit strange. We've defined lambdas for each operation, stored those in a map, keyed by the names of the operations. When we encounter an operation, we're going to execute the operation that corresponds to that name on the current stack and push the result of that operation executed on the stack back onto the bottom of the stack. And that's how RPN works, that every time we perform an operation, we pop a number of operands, compute the result of the operation, and push the result back on the stack. And so the way that RPN works as well is that if we have a successful RPN expression, if we have a valid RPN expression, then there should be a value at the bottom of the stack that we can pop as our result. And so I'm going to say return stack.pop to get our final value from the stack. And that'll be our answer, the thing that remains on the stack after we've done all of the other operations. So now I'm going to go ahead and print this, the result. And now, the result of this expression that we're expecting is going to be 7 times 3 is 21 plus 4 is 25. So if this worked and if our functional interface was defined correctly and we defined all our lambdas correctly, that is what we should see down at the bottom. And there we go, we've got 25. All right, great, it worked. Cool. So now we can successfully evaluate basic RPN expressions, and we can do cool things with them, right? Like, for example, here we've got operations that have to flip the numerator and the denominator. All of these operations are binary. We'll get to the way that we deal with operations that take more than one operand in a little bit. But right now, I'd like to see what happens if the user gives us an invalid expression. So what if they then try and subtract from the stack when we do not have anything on the stack, right? So for example, so if we try and subtract the numerator from the denominator, if we try and subtract the subtrahend from some value, that value to subtract from won't exist. And so we are going to get currently a no such element exception, saying we can't remove the head of an empty deck. And, you know, honestly, that kind of works, right? Like, that's honestly not the worst error message in the world, but I'd like to give the user something a little bit more useful. And so what I'm going to do is I'm going to say that we're going to put this in a try-catch block. And if I get a no such element exception, oh, and I've got to give that a name in Java, right? Then I'm going to give them a more friendly message. I'm going to say system.error.println insufficient operands to perform operation. Something like that. And so now if the user tries to execute something that's invalid, instead of getting a scary Java stack trace, they'll just get a message that says, hey, can't do that. Bad. And now, something that would also be nice to do would be to actually tell the user what operation failed, but, you know, that's a little bit outside of the scope of what we're doing right now. Because the next thing that I want to do is something that's a lot more fun. and I want to make this interactive. So having a calculator we plug values into is cool, but I would actually like a calculator that I can type into. And so I'm going to go ahead and do that. And so what I'm going to do is I'm going to say, alrighty, so try. And now this is currently going to be an infinite loop. And I know that we try and avoid infinite loops if at all possible. But we're going to do that right now. And Exposeed asks, what if it's the other way around? Insufficient operators for all the operands. So that actually, that's a really great question. And that really kind of depends on your problem scope. So you can, I mean, you could potentially return an error if there were too many values left over on the stack, but I think it's a little bit more intuitive, actually, to just return the thing that's at the bottom of the stack. And if there are extra values, we just discard them. I mean, to me, that makes a little bit more sense. And so we've got a while loop here. We're going to say, okay, I'm going to make a new scanner to get user input from system.in. Now what I'm going to do is I'm going to say, okay, so I'm going to get a new line. So I'm going to say, let's see here. So, string, well, actually, I'm sorry. I want to make the scanner outside of the loop. And I'm going to say, okay, so string, expression equals input.next line. And I know that we don't actually currently have a way to stop this calculator. We'll get there in just a second. And now what I want to do is I just want to print the results. So I'm going to say system.out.println calculate expression. And so now, instead of having to pre-program the expression that we want to compute, I can type it in. So if I want to say 7 times 3, I get 21. If I want to do that previous expression, 7 3 times 4 plus, we get 25. If I do something wrong, then it tells me there are insufficient operands, and it stops the loop. And honestly, you know, that's something that we should actually probably put inside the loop so that the user can keep going. And so I'm going to relocate this try-catch block a little bit. I'm just going to go ahead and put this inside of the loop and then reformat this code. So now if the user tries to put in an invalid expression, they can potentially fix it later. So 4 5 plus is 9. And so there we go. Now I've got a basic RPN calculator that supports all of the unary operations that our hearts desire. But what about other stuff? What about, you know, what about, all the binary operations that we desire? What about unary operations? What if we want to negate something? Well, that's actually pretty simple. All we're going to do is I'm going to say, I'm going to call this operator neg, and all we're going to do is return the negative value of the thing that's on the bottom of the stack. There we go, and that's how we support a unary operation. Because each one of these lambdas has control of the stack, it can implement the stack operations however it wants, using pushes and pops and all of that, and there's nothing that's too atrocious in terms of overhead to support different arinesses, different numbers of operands for different operations. Disabled account, let's go for a tertiary. Yeah, why not? Let me think of a good, let me think of a good, trinary operator. Oh, I've got one. Let's implement conditionals. Why don't we do Exposeed logarithm? Oh, we could do logs. Although, wait, could we? No, because that would just be, like, value base. But in terms of trinary, disabled account, what I like actually is, or ternary, yeah, they are ternary, yeah. Yeah. Ternary, Mega Crafter J is correct. Yeah, they're called ternary operations, but yeah. Anyway, thank you for the correction. What I'd like to implement is a conditional. Something that a calculator doesn't normally have is the ability to essentially have what we would call, yeah, ternary operation. Where we would say that, you know, if some value, or if some truthiness X, else Y. And now this is going to require two things of us. It's going to require a definition of truthiness on an integer stack. And the way that I'm going to define that is to say that on this stack, 0 maps to false, anything else maps to true. And this is similar to once you get into maybe a computer architecture course, you'll learn that this is how C and C++ handle truthiness. Java doesn't do this, but it's a pretty standard thing for us to do. Yeah, it's how C does it. Exactly, Exposeed. Yeah. And so what I'm going to need to do is I'm going to need to define a few things. I'm going to need to define comparison operators so that I can actually get a truth value. And then I'm going to need to define my ternary. So, you know what? Let's do it. Let's see. So operations dot put, and let's say that I'm going to define less than. I'm going to say, okay, so we want to say x is less than y, right? So x is less than y, which means that we would need to actually, let's see here, what are we going to need to do? We are going to need to flip the values on our stack again, right? We can't just say pop less than pop. Yeah, that's not going to work quite as well. But that's okay. We can do this again by just storing, let's say, our second value, and then return stack.pop is less than that second value. So there's a binary operator. And, you know, something that we could do later is we could add other comparisons. But for right now, I'm not going to bother. Oh, and I've actually got an error, which is return st.pop less than second. I'm returning a Boolean. Oh, although actually, yeah. Actually, something that I like better, as MegaCrafter and Exposeed both said, can you do pop greater than or equal to pop? And you could, right? These operations are reversible. And I actually like that a lot better, yeah. So to implement less than, I can essentially say that something is not greater than or equal to. And so I can actually say st.pop is greater than or equal to st.pop. And now in Java, yeah, we don't have implicit conversion of integers to Booleans, but you know what? That's okay, because I can just use a ternary. And so I can say st.pop greater than or equal to st.pop, 1 else 0. And, you know, it would be nice if I could just cast these directly to int, but that's something that the designers of Java decided was not something they wanted to include in their language. And we can do this for all of the other operations too, but we're just going to stick with less than for now. And now, the really fun one is we're going to implement a ternary. And so what we want to do is we want to have 3 values, and I'm going to define the ternary as having the following operands on the stack, where this is the bottom of the stack. It's going to have the condition, which is our Boolean. It's going to have the truthy value and the falsy value. And so essentially, if you wanted to say if 3 is less than 4, then it would look something like this. 3, 4, less than, or actually, let's do this as a ternary. 3 is less than 4, ternary, return 5 or 6. You would say 3, 4, less than 5, 6, if, is what that expression would map to. And so now, we'll go ahead and say, alrighty, so I'm going to say that my falsy value is going to be stack.pop. Truthy value, also stack.pop. And then my condition, also stack.pop. And now I'm going to return. So if the condition is 0, then I want to return my falsy value. Else, I'm going to return the truthy value. Great. So now we've got this, and I need to give this a semicolon, obviously, to end the line. But now we've got a ternary in our RPN calculator. Something kind of powerful that we might not have had in simpler calculators. So, what we'll do now is go and test this. And I'm actually going to use this exact expression. I want to determine if this expression as is will work. And noting, of course, that 3 is less than 4, so I should get 5 as my output. So let's do it. Let's go ahead and run our code. Go ahead and paste that. Oh, it's not going to let me. That's fine. I'll just say, oh, it appears that my input window has frozen. That's okay. Here we go. 3, 4, less than 5, 6. If we should see a 5. And we do. Great. And now if I flip this, 4 is not less than 3. So I should now have a 6. There we go. Great. And now I'm going to do one more thing here. And it's very simple, but I'm going to say that if the expression equals, and let's just say that quit is our exit command, then I'm going to stop the program. And now I can write this in a more elegant way, or I could say Boolean running equals true, and say while running, and you know, say that if it equals quit, or actually just say that running equals, well, no, I'm actually going to do it this way. Then I'll set running to false. Otherwise, then we evaluate the expression. That's something that we can do just to clean up the code a little bit. But so now we have a calculator that is usable in that now if you do an expression and you're like, okay, cool, that worked. I've done my computation, I want to quit. We can now exit the calculator without having to kill the program. So this is the basic kind of structure of a functioning real-world RPN calculator. And, you know, if we were to want to continue to implement this and add more and more and more features, we could totally do that. But we're getting on a little bit long in time today, and so I think that we're going to cut the stream right about here. If anyone has any questions about this problem or anything else we've done today, please post them in chat. If you just want to chat about something random, you can also post that in chat. But yeah, there we go. There's an RPN calculator. We could keep working on this. We could end up writing a dialect of fourth if we wanted to. And yeah, Exposeed, I'm definitely gonna post a GitHub link. Right after we're done, I'll probably end up putting up kind of a conclusion slide and let you listen to some nice organ music. And then yeah, I'll post the GitHub link in the stream chat before I stop the stream. Totally. Kappa votes, are you always this jolly? Do you ever get into bad moods? I mean, I do. Like, I have days where, you know, I'm not as, not as enthusiastic, might we say, or not as light, in a way. But, you know, I always try, and, you know, in my opinion, it's very hard to learn something unless the person who's teaching it to you seems like they enjoy what they're doing. Right, and so anytime that I'm, you know, just interacting with y'all or, you know, just kind of, you know, trying to show someone something, I always try and make sure that I'm giving them the best possible, you know, impression of the thing that I'm demonstrating. In addition to the fact that this type of stuff I just find very fun and interesting. I like, you know, interacting with y'all, and this is my first stream, but I'll say that I'll definitely do a lot more in the future. This was, you know, a great time. I had a lot of fun. I hope that you all did as well. And so yeah, and that's kind of our, yeah, that's our goal. And oh, our music has stopped. Let me put something back on. There we go. And so yeah, am I always this jolly? No, I'm not. But I had a lot of fun today. I hope that you did as well. And so, you know, I would say that, yeah, I was definitely in a good mood throughout this whole process. XRC, great stream. Thank you. I'm glad that you enjoyed it. Do I have a schedule figured out? That's a great question. I know that I'm likely going to be streaming on the afternoons on either Saturdays or Sundays. Which one of those days it is, I haven't quite determined. I will definitely update my, account on Twitch once I have decided that. And so, yeah, so I will definitely post, the schedule up on Twitch. And if you're in my student base, then I will also let you know when streams are going to be on. But yeah, so yeah, I will definitely figure out a schedule and try and stream fairly regularly. There will be at least one stream a week. And Prince Logic, I'm glad you had fun. I hope that, yeah, I'm glad that you had a great experience with this. I certainly did. And so yeah, so if you're not one of my students and you want to know when I stream, then totally feel free to give me a follow. I'm not super familiar with Twitch, but I think that part at least doesn't cost any money. And so yeah, you can give me a follow, support the channel. And yeah, I guess that's about it from me. If y'all have anything else you want to discuss, feel free to post it in chat. Otherwise, I'll take a hike for today. It's the subscribing that costs money. Yeah, okay, thank you, Exposeed. It's the subscribing that costs money. Yeah, that's what I thought. That's true. Okay, so yeah, so I'm gonna go ahead and, yeah, throw all this stuff on GitHub right now. And I will keep monitoring the chat as y'all talk and while I do that, but for now, I'm gonna go ahead and put up our ending slide and, yeah, take it from there.